Yes, good afternoon to all. Am I audible and my screen is visible?
Yes, sir, it is visible and you are audible.
Yeah, thanks. Yeah, I think that you are all aware of machine learning, the basics of machine learning. So just I'll give you a brief
Sir,
introduction about the machine.
so
Yes,
sorry
sir.
to interrupt you. Sir, you can have this full screen so that
Sir,
the
actually, it is
participants'
not
visibility will be better.
functioning in my laptop. I
Okay,
don't
okay, then
know why it
it's
is
fine.
not
Sir.
functioning.
It's fine. Then you
Yes,
can
sir.
just zoom it.
I have tried it, but it is not coming. I don't know why.
Yeah, it's okay, sir.
Okay,
Okay, you can start. Sir. Thank you.
okay, sir. Okay, so just we can start with the introduction of machine learning and then we can go to the naive Bayes algorithm. Okay, today we will be covering the intro of machine learning, then detailing algorithm, and we'll be having a hands-on session based on these algorithm. Okay, so already you know about machine learning, I think so. Can from any one of you can inform me what do you mean by machine learning from your side? Okay,
Sir, the participants are on mute. They can ask the question whenever the tag will be completed. Sir. So you can
okay,
continue.
sir. Yes, yes,
Yes, yes, yes.
yes, sir. Thank you. So, it's a machine learning is one of the subtopics in the artificial intelligence. It's a subfield of artificial intelligence, am I right? So, we are going to train the machine to learn. As a human, we know if I see a particular picture or a particular video or audio, I can recognize even after some days or some months or some years, am I right? I can recognize a person or some other thing. But this is not the case with machine, am I right? We the people has to train the machine, and based on their training it has to produce the output. Am I right? So that is the main concept of machine learning, and the formal definition I have given you. So it is going to learn from the experience based on the given tasks, and it will perform the measures. So what we are going to measure in sense, that is the thing. So I have given an example here. See, suppose this is the two examples. So we want to play chess. Okay. Here the task is we are going to play chess, and the experience is here. What do you mean by T? T is nothing but the task, and E is the experience, and P is the probability that it is learning. Okay. So T is the what is the task? Our task we have to play the chess, and E is the experience. Several games has been trained to the machine. So by playing, interacting with the users, we are playing several chess games. Am I right? So that is the experience. So based on the previous games, it will earn some experience, and based on the experience, now if a new player is coming into an existence, and this machine will compete with the new player, and it will provide the probability of winning the user. Am I right? So that is the case. So second case, similarly, you are going to the machine is going to recognize a cat. Here the task is it has to identify cat as a cat picture. Am I right? And here is what is the experience. So we have to train the machine with several images of cats. Am I right? So if I train the machine with several images of cat, and if I give a new image which has not been trained, then the machine has to recognize that it is a cat. Am I right? So that is the thing of machine learning, and this is the overall definition of machine learning. Okay, this you might have learned in several previous classes. So as I'm making it simple with an example, so what is T and E and P? Okay, so next we are going to see about the types of machine learning algorithms. The machine learning algorithms can be classified into three. One is supervised, unsupervised, and third one is reinforcement learning. So if it is supervised, we will be having a predefined labels. For example, we can take a COVID prediction. Okay, so if the person is affected by a COVID, we will have two class labels. One is positive and another one is negative. Okay, so based on that, if I give any lungs images to the machine, from the lungs images, it has to identify whether the patient is having a positive COVID or it is a negative situation of COVID. Okay, so we will predefine the labels. So we will be predefining positive and negative labels. Okay. So here the labels with the predefined labels, we have to map with the given labels. So that comes under the supervised learning. It is like teaching students with the help of the teacher. That is comes under the category supervised learning. The unsupervised learning, here we don't know the predefined labels. There will be no predefined labels. So based, I will be giving some data to the computer. The computer and this unsupervised algorithm, it itself defines the classes. So same way, if I give the images of lungs to the algorithm, unsupervised algorithm, based on its own experience, it will classify it whether it is a positive or COVID. We will not define any predefined labels. Okay, but in supervised learning, we have to define. Okay, that is the thing. And reinforcement learning is a booming technology now. So already you might have learned about the car, am I right? That is self-driving cars. Okay, so the self-driving cars are nothing but that cars won't have any drivers. If it has to drive from particular source to destination, it has to learn itself, and if it makes any mistake, so based on the mistakes, it will get punish activities, and based on this we will be getting rewards. If it is working correctly, the rewards will be given to the machine, like that. So it has to learn it own by with the help of the state and actions from the environment. Okay, so these are the three predefined classifications of machine learning algorithms. Today we are going to see the supervised learning algorithm. Under that we are going to cover naive Bayes algorithm. Okay, so I have given whatever I have told that was in this slide. Okay, so next, in detail, I have given the classification. See, under supervised learning, we are having two things: regression classifier and normal classification. So today we are going to cover classification. See, regression is based on the continuous variables. Continuous variable in sense it will be having real numbers, decimal numbers, and all those things. Am I right? So based on that classification, we'll go for regressions. So under this regressions, we are having decision tree and random forest. Then in the regression, linear model and polynomial models are there. But in the classifications, we are purely going to classify the categorical data. Just now I have told you, am I right? If it is a COVID, we are going to say whether it is yes or no. So that comes under the categorical data. So classifications, under this classification algorithm, we are going to see naive Bayes today. Okay. So that is our main theme. And next, before going to naive Bayes, we need to know how the naive Bayes algorithm is getting functioned. Okay. I think, am I audible?
Yes,
Yes,
sir.
sir, you are
Yes,
audible clearly,
sir.
sir.
You are.
Yeah. Okay. Okay. So before going to this algorithm, we need to know how this algorithm is functioning. So based on what concept it is functioning. So this naive Bayes algorithm is purely functioning on conditional probability. So this conditional probability is defined by the theorem called Bayes theorem. You might have learned these in a probability and statistics subject, I think so. So we will see what is conditional probability and how this Bayes theorem is getting functioned. Okay. So before going to the Bayes theorem, just we will have a recap about the probability and statistics. Okay. See here. So suppose this is our task. So we are having two coins. Okay. These two coins has to be tasked. Okay. When I'm tossing these two coins, what are the possible sample space I can get it? Either these two coins can produce head. Both the coins will produce a head when I'm tossing, or it can produce first coin may have head and second coin may have a tail. Am I right? And if I'm tossing again, what is the other possibility? First coin may have tail and second coin may produce head. Okay. Or finally, both the coins may produce a tail. So these are the sample spaces. So you want to know sample space, the possible probability that can be taken from the given problem. So what is our problem here? We are going to task at two coins. So on tossing two coins, these are the sample spaces we will be getting. Either two coins will have head, or one coin is head, another coin is tail, and one coin is tail, another coin is head, like that, or both the coins will produce tail. So now see how from this we are going to define the probability. So what is the first question? See, probability. P is nothing but probability of getting two hits. So from the sample spaces. So how we are defining the probability? So based on the condition. So what is our condition? Probability of getting two hits. So this is the total sample space. So the probability condition divided by the total sample spaces. So what is the total sample spaces? 4. So what is the probability of getting two hits? That is only one choice. Am I right? First choice, head and head is the two hits. So 1 divided by 4. Same way, second question, see, at least one tail. So the probability of getting at least one tail. So see, from this given thing, HT. So this is having one tail and TH is having one tail and both here TT is having another tail. So there are three probability of getting at least one tail. So divided by total sample space. So what is the total sample space? 4. 3 divided by 4. Same way, see third and fourth condition. Here comes the conditional probability. So this is the normal probability. Generally, we will define. Now we are going to work on the conditional probability. So here, what is the thing they have given? See, second coin being head. Okay, given the first coin is tail. So condition probabilities, we can define the condition probability by CP of, okay, A given B. So what is A given B? So A given. So here we have given, already we have given the condition of B. Based on that, we have to define A. Okay, so that is the second coin being head, given the first coin is tail. They have given the condition that the first coin is tail. So here, which is that condition? Third sample space choose is up to that. Am I right? T is the first coin that is having tail, and the second coil is going to be a head. So among this, so here given condition is C. They have given a conditional probability. What is my condition probability? First coin should be a tail. So here, which first in which of these sample spaces first coin were tail? These two sample spaces, TH and TT. Am I right? So here, this is the first coin is tail, and in this sample space, first coin is tail. From this given condition, we are going to take the second coin as head. So among these two, which is correct? This is correct. So 1 divided by 2. We are not going to take the total sample space. So we are going to choose the sample space based on the given condition. So that is called as condition probability. Here, what is the condition? B. Okay. So B is the condition, and with the given condition B, we have to find the probability of A. Okay, can you able to understand what is the condition probability now? Or still you're having doubts in this third question? So the conditional probability in sense, they will give the predefined condition for the sample spaces. Am I right? So given they have given the first coin is tail. So already the first coin should be tail. So among the 4 sample spaces, only 2 condition is suitable for that. So based on the given condition, first coin tail will be TH and TT. So total available sample spaces from the given sample space will be 2, because only these 2 possibilities have 2. First coin is tail. So here you will be dividing by 2. Then what is the probability we need to find? Second coin being head from that given condition. So which is the second coin being head? So this is the third sample space. It's going to have second coin as head. So 1 divided by 2. Same way, fourth probability. This is also condition probability. Getting 2 hits given first coin as head. So here in these first two sample spaces, the given coin as head is first coin is HH and HT. So the total sample space will be 2 divided by, so 1 divided by 2 will be nothing but what is 1 here? They have given the probability getting 2 heads. So this is the only choice, getting 2 heads. So 1 given 2. So are you able to understand now what is conditional probability now? So for these conditional probability statements, we can use a naive Bayes algorithm. So that is the main theme of naive Bayes. Okay. Am I making sense? Is it clear?
Yes, sir.
Okay. So this is the definition of your Bayes theorem. It gives the conditional probability of event A given a event B. Okay. So this is the formula C. They have given some condition B. Based on the given condition B, we have to define the probability of A. So that is the Bayes theorem. So the formula for that is P of B given A, then P of A divided by P of B. So here, what is that P of B by A? A by B is nothing but conditional probability of A where given B. But B by A is conditional probability of B given A. And P of A is probability of event A and P of B is probability of event A. Okay, so event B, this is B. Okay, so from the example, what we have seen earlier, see, this is a normal probability condition, and these next two is based on the conditional probability. Okay, so for these conditional probability, for predicting these conditional probability, we'll be using Naive-Bayes algorithm. Okay, so let us have how this Naive-Bayes is going to. You can see it in detail. So after completing this, we can directly go to the hands-on session. Okay. So I have told you this Naive-Bayes is one of the machine learning. Under machine learning, it comes under supervised learning. And under supervised learning, there are two classifications I have told. One is normal classification, another is regressive classification. This Naive-Bayes comes under classifications of supervised learning. Okay. So where it is being used. So for what are all the applications we can use this Naive-Bayes algorithm? See, especially it is used in weather predictions. Okay. So it is used in weather prediction. And next, we can use in face recognition, speech recognition, and of course in antivirus. Okay. So for these probability, so how we are using it in antivirus? Can anyone? Obviously we'll be using a weather prediction. So how we are going to use it in weather prediction? See, they will give a statement today. If it is cloudy, okay, and sun is not much hot, then definitely it will rain. Am I right? So like this, we can define a probability. So based on that, the weather can be predicted. So for these purpose, we are using. So in antivirus also, we have to predefine the virus structures. So if the structure is so and so, based on this condition, then obviously it should be a virus. Am I right? So for that purpose, we can use it in antivirus predictions, then face recognition and speech recognition. All those situations, we will be using this Naive-Bayes algorithm classifier. Okay. So now again coming to the formula, Bayes theorem can be used in Naive-Bayes classifier. See, so this is the Bayes theorem. Am I right? So here P of C slash X. So X given X, we have to predict the probability of C. So that is the thing. So this is called as posterior probability. So what do you mean by post? We are going to find this. Am I right? Find this later. Hence it is called as posterior probability, and this is likelihood. So likelihood is in sense for a given condition C, what is the probability of X? That is called as likelihood. And probability of C is class prior probability. So this is prior probability we know earlier, am I right? And same way, predictor prior probability. What do you mean by predictor prior probability? Probability which we have given as a condition is called as predictor. So based on this prediction, we have to find what will be the probability of C. So which is given here condition X. So that X is P of X, probability of X is called as predictor prior probability. So prior in sense, we will calculate this P of X and P of C in prior. So hence it is called as class prior probability, and this is predictor prior probability, and this is likelihood and posterior probability. We will see it in detail, what is likelihood and class prior probability, all these things, okay, with an example. So let us learn this algorithm with an example one, okay. So this is our task. See, they have given three columns. Okay, day, discount, and free delivery. So these are our data sets, input data sets, and based on this input, with the help of the Naive-Bayes algorithm, we have to predict whether the person will buy the product or he will not buy the product. Okay, something, we are going to purchase some product. Okay, so whether the person will buy the product or will not buy the product, that is the output. So this is the output we are going to predict with the help of Naive-Bayes, and the given input is these are the things. So here day is, they have given day, three conditions are there: weekdays, weekend days, and holidays. And discount is if there is a discount or if there is no discount. And for free delivery, if it is free delivery, yes, and if it is no, then there will be no free delivery. Okay, so we have to find all the possibilities of buying these products. Okay, so we can check how we are going to do this. So this is the predefined table. So this table contains 30 rows, but as of now, in order to visible, I have taken only 15 rows. Okay. So these are the days. So I have already told you days has three conditions. One is a weekday, if it is a weekend or holiday. Same way for discount, we are having two probability, that is yes or no probability. And for free delivery, we are having again two probability, yes or no. So when I have given these data, day, discount, and free delivery, we have to predict this. Say we have to predict this output. So with the help of the neighbors algorithm, we are going to predict whether the person will buy the product or not. So this we are going to use it as training and testing. So some of the data will be used as training and some of the data will be used as testing. So what is the difference between training and testing? You might have learned in the previous classes, am I right? From the morning. So as I have told you in the introduction of machine learning, so we have to train the machine, am I right? Like human being, the machines won't have any IQ. So we, the people, has to train the machine with a set of data. So the data we are using to train is called as training data, and we have to test it whether it is predicting correctly or not. So for testing, we will be giving the data which we have not used for training. Those data are called as test data. Am I right? So can you differentiate between training and testing now? So training, what we are going to do, so we have to train the machine. Am I right? Train data is used for teaching. Am I right? Teaching the machine. And what do you mean by test data? Test data are nothing but the data that are not used for training. So if I have trained some data, if I'm using the same data as a test data, then obviously it will produce 100% result, right? So that is not the case with machine learning. So if it is a test data, we have to give those test data which you have not used it for training. Okay, that is the main purpose of testing and training. So all the data in machine learning will be split under these two categories, training and testing. Okay, so now we can see this. So we have to convert that given table into frequency table. So how we are going to convert these three? We are forming three. What are the three inputs? We are having discount, free delivery, and day. So these are the three inputs. For these three inputs, what is our target data? Whether people will buy or not. Okay. So for see discount, you are having two probabilities yes or no, and for free delivery, you are having two probabilities yes or no, and for weekdays, you are having three probability conditions: weekday, weekend, and holiday. And this is the thing we are going to predict buy. So yes or no, we are going whether the people will buy the product or not. So under discount C, yes, and buy should be yes. So how many data are there in the table that we have to take it? See, under now we are going to take the discount, am I right? So we have to take the data which is yes, and buy purchase is also yes. So like that we have to count each and everything. So yes and yes. Now we are going to do manually. I'm explaining how the naive Bayes is working. Okay, but when you are using the naive Bayes algorithm, automatically it will take all those things. So first the discount, yes, and purchase is also yes. So here this is 1, 2, and this is 3 and 4, 5, 6, 7, 8, 9. So as of now, 15 days. From the 15 data, I have 9. So remaining 15 days I have not shown you. So totally it is having 19. So this is the frequency table. So for each and every input data, we have to compute a frequency table. For discount, I have computed. Same way for discount, yes, and purchases, no. Only one data is there. And next, we have to take discount no and purchase 5. If I purchase yes, so there are 5 data, and discount no and purchase no, there are 5 data. If I add these all these data, you will get 30 because only 30 rows are there in the table, right? 19 plus 1, 20, 20 plus 10, 30. Okay, so that you have to make it clear. Same way for the frequency table of free delivery. Free delivery also you can see this table. You can look into this table. The free delivery, what are the things you are having? Only two things, am I right? Yes and no. Okay, yes and no. You are having only yes and no. And purchase, obviously, you are having two conditions, but yes or no. So for that also, the frequency table is we are going to form the frequency table. Okay. Likewise, when the free delivery is yes and the purchase buy is also yes, there are nearly 21 data in the table. Same way, free delivery yes and purchase no, 2 data. And free delivery no and purchase 3 data. And free delivery no, purchase is also no, 4 data. So if I add all together, what you will get? 21 plus 2, that is 24, 23, 23 plus 7, 30. Same way, we have to do it for frequency table of day. So in the day, we are having 3 conditions: weekend, weekdays, and holidays. So for this, here also for buy, you will be having 2 probabilities. One is yes and no, right? So here 9, here 2. So weekdays, those who are buying the product, 9. And weekdays, those who are not buying the product, 2. And weekend, those who are buying the product, 7 members are there. And weekend, those who are not buying the product, only 1 person is there. And holidays, those who are buying the product, 8. And holidays, those who are not buying the product, 3. So altogether, if I add these things, you will get 30. So first thing is it will calculate the frequency table for the given inputs. Okay. Then after calculating the frequency table, next we have to define the condition probability. Right? How we are going to define? Now based on the data set containing 3 input types. So what are the input types we are having? Day, discount, and free delivery. Okay. So we have to calculate the frequency table. After calculating the frequency table, so this is the probability condition. How we are going to define? The probability of A given B. So that is the Bayes theorem, am I right? Here, which is B? See this discount, free delivery, and day. These are given, am I right? So these are input data. So what are all the input data? That is considered as B. So here discount, free delivery, and day are considered as B. And what we are going to predict whether the person will buy or not. So that will come under A. So we are going to predict the probability of buy, whether they will buy or not, when the data are given as discount, free delivery, and day. So are you clear with the condition probability now? Okay. Do you have any doubts in this? Is there any doubt? Shall I move to the next slide?
Yes, sir.
Okay. Okay. So these are the things. What is the first thing? So first we are going to find the frequency table from the given data set. For each inputs, we have to find the frequency table. After finding it, then we have to form the conditional probability. So what is the conditional probability here? We are going to find whether the product people will buy the product or not. So that will be a A. And what are the inputs they have given? That condition we have to take it as B. Okay. So now we are going to find next likelihood table. I have told you P of A given B, am I right? So we need to find that likelihood table. Likelihood is nothing but P of A given B. Okay. Sorry, no, P of B given A, am I right? That is the likelihood. So already we have defined here what is likelihood. See, P of here my condition is A given B is, so here A is a probability which we are going to find, and here C is a probability which we are going to find. X is given probability, and likelihood is just opposite. From the given data, we are going to find the given data from the probability which we are going to find. That is called as likelihood. Just the opposite of posterior probability. That is the likelihood. So just next we have to define that. Okay. So how we are going to form the likelihood table? So that is the thing we are going to do here. See, just we can take the 3 inputs. What are the inputs we are having? Days, weekdays, and weekends. Okay. So if I take days, so there are 3 conditions: weekend, weekdays, and holidays. Okay. So this is the frequency table already we have found. So now we are going to add this. So in the row wise we are going to add, and column wise also we are going to add. So from the frequency table we can do like this. The frequency table can be converted to likelihood table. Okay. So see here, weekdays. So what is the total data? 9 plus 2, 11. And weekend, what is the total data? 7 plus 1, 8. And holidays, 8 plus 3, 11. Same way, those who are buying the product, totally 24. And those who are not buying the product, totally 6. So if I add these rows and these columns, this column and this row, obviously the data will be 30 only. Am I right? So how we are going to convert this frequency table into likelihood table? So this is very easy. This is the total sample we are having, 30. Am I right? So what is the total sample? 30. So we are going to divide all the things with the total samples, 11 by 30, 8 by 30, and 11 by 30 here. And same way here, 24 by 30 and 6 by 30. Very clear? So we are getting the probability of these things. So this is called likelihood. So how we are getting the likelihood? See, this is B data, right? Weekday, the weekend holiday. These are B data. So we are going to find P of B by A. That is likelihood. So obviously we are getting that. P by A is total data is total samples we are getting is 30. So these are the likelihoods. Are you clear? So see probability of B. So P of weekdays. Okay. So first we are taking weekdays. So it is 11 by 30. When I divide 11 by 30, the value will be 0.37. Obviously, the probability value will not be greater than 1. Right. So it is 0.37. When I take P of A. So what is the probability of A? Probability of A in sense those who not buy. Probability of people those who not buy. So it is nothing but 6 divided by 30. The product, the people which who not buy, right? 6 divided by 30. So zero point 0.2. Then we are going to calculate B by A. So first we need to calculate this. So I will paste the formula here, then it will be easy for you. Take this. So how we are going to calculate this likelihood? Just we will be having P of P. P of P is nothing but P of A, and P of X is nothing but P of B. Okay, so that is the thing. So we are going to calculate P of B and P of A, then we can get PB by E. So that is the thing we are doing here. So what is P of B here? P of B is nothing but X. So P of B is buy or no. So here we are taking sorry, P of B is your data weekday. So what is B here? Probability of B is in first we are calculating for day, right? So from the day I am taking only weekday. So what is the weekday here? 11 by 30. Okay, so the probability is 11 by 30. Same way, we have to calculate the probability of B for a weekend and holiday. So for just one example I have taken. Similarly, you have to calculate for P of weekend and P of holidays also. Okay, so now we have taken weekdays, and in the weekdays, next what is the P of X? Just we are going to take those who not buy. We are going to calculate not buy. Okay, so weekdays by no buy. That is the thing. So weekdays by no buy. What is the thing weekdays? So 2 by 6. Okay, that is the condition. 2 by 6, no. So 2 by 6 is 0.33. So this is the likelihood value. They clear with these things. So same way, next we have given C, P of weekdays, no by. We have calculated weekday by no by. Then no by weekday. We are going to take A by B. So we want to predict A by B. So this is our condition property. We have to predict A. Am I right? Bayes theorem. By Bayes theorem, this is our formula. P of A mod A given B. So what is the formula for that? P of no by when given weekdays. Okay. For that formula is, so here which is A? A is nothing but not buying, and B is given the day. In that day, I am taking only weekdays. Okay. So how the formula looks like? P of B by A. So here B is weekend and A is no buy into P of A. P of A is here no buy divided by P of B. So what is B? Weekdays. So all the things we are getting. P of weekday is 0.33 and no buy is 0.2 divided by 0.367. So it will give the value, the probability is 0.179. Okay. So this is the likelihood, this is the conditional probability of P of A given by, when my input is, we are going to take only days, and in this day what we are going to do, in this day what we are going to do, we are going to take only weekdays, and in the weekdays we are going to calculate only the product which was not bought. Okay, so can you able to understand how it is performing? Likewise, we have to calculate all the possibilities when I take weekend and those who are buying yes and those who are buying not. So that like this, we have to calculate all these things. Then holidays, those who are buying, and holidays, those who are not buying. So when we complete these three things, day will be over. Then similarly, we have to calculate for what are the other tables we are having. We are having discount and free delivery. So in the discount, we have to calculate for condition probability of when given discount. Okay, so here this will be B and A will be two condition. When A is equal to yes and A is equal to no. For this, we have to calculate. Same way for discount also, we have to calculate yes and no. Are you clear? So first we are going to calculate frequency table. Then from the frequency table, we are going to calculate the likelihood table. If we calculate these two things, we will get all the values of the Bayes theorem formula and we can easily calculate. So this is what the Bayes theorem is going to do. Okay. So now I'll give you a task. Can you calculate it? See? So this is the thing. So my question is, whatever I'm giving here is B equals to day should be holiday and discount is yes and free delivery is yes. Okay. So this is the given B. And for that, you have to find the probability of not buying. So what is my condition probability here? A given by A when B given. So how can I make this formula? So what is my condition? A is no buy and B, whatever I have given is B. Day should be holiday and discount should be yes, free delivery should be yes. At this condition, you need to find the probability how many people are not buying. Okay. Now, are you clear with the condition probability now? So condition probability means you will be giving a given condition. Based on the given condition, you are going to find a probability which they asked. Here they have asked about not buying. So A is not buy and B is whatever they have given. Day should be holiday, discount should be yes, and frequency should be free delivery should be yes. So see here, if I take this, what is the formula? So we have to calculate like this. So discount, first we are going to take all these things. B by A. First we need to take B by A, am I right? How many B's are there? Three conditions are there. So first B is discount is equal to yes and A will be no. Then second is free delivery is equal to yes and A will be no. Am I right? Then third is day is holiday and A will be no. So this is the likelihood. So how many likelihood we have to calculate? Three likelihoods because three conditions are given in B. Okay. Then into P of A. What is P of A? That is not by. So this is the formula. Am I right? I'm going to take this formula. Wait. It will make you sense. So here I am pasting this formula. Okay. So see here, this is the formula. Am I right? So here what is my B? Under B, what are the things we are having? Days is equal to holiday, discount is equal to yes, free is equal to free delivery is equal to yes. So here B is this is the thing, and A is so I'll tell you clearly. So this is B, right? So this is B, and what is my A? Here A is not by. So A is given. So this is the previous thing. Okay, so we can take this example. So here they have A changed A is equal to by. So by the given condition, so you have to find. So when the given condition is holiday, discount is equal to yes, free delivery is equal to yes, how many people are buying the product? So here, what is the given condition? B is the given condition. Based on the given condition, we need to define the probability of A. A is we are going to calculate the probability of how many people are going to buy the product. Okay. Then obviously see P of B by A. So here, which is P of B by A? Uh, So here P of B by A, B by A is this is P of B by A. So first three are B by A. So first three up to this is P by A. So in B, how many conditions are there? Day is equal to holiday. So for that we need to find day is equal to holiday and by. So first discount. See they have taken discount. Discount is equal to yes. Buy is equal to yes. Then next they have taken free delivery. Free delivery is equal to yes. And next buy is yes. Then next again we are having day is equal to holiday and buy is equal to yes. So up to this P by A we will have three probabilities, right? Likelihood, three likelihoods we have to calculate. Then into P of A. Here, what is P of A? P of A is yes, buying yes. So that is A. And next, B will be all the things. So discount is equal to yes, free delivery is equal to yes, and day is equal to holiday. So this is B. Okay, all the three possibilities we have to take. Are you clear with these things? So how we are going to get the likelihood values? By likelihood tables. Okay. And how we are going to get the frequency table? So first we will be computing the given data and we have to count individually. So this is the functioning of naive Bayes. Are you clear with these functioning? So when I give new data, see, suppose, so this is the given data. So with this table, we are having the given data. So when I'm giving a new data which is not in this table, suppose assume in holiday here yes and no are there, yes and no are there, both the people are buying. But when I'm giving holiday yes and weekend is equal to no, then purchase is equal to no. Like that, if I am giving no new data, then it should find based on the conditional probability. Am I right? So this is the training data. So we can split this training data itself into two. So first 15. So what is the splitting rate of train test split? The very good rate should be 80-20 or 70-30 or 60-40. So in this thing, some of the peoples may split. So 60. So when it is 60, testing will be 40. When it is 70, testing will be 30. When it is 80, testing will be 20. Okay. So in this range, we have to split our data, given data. So 40, 30, 20. Okay. This is the percentage of split. So this is the total 30 here is when I'm splitting it 60, 40, how many data we will be getting? In how many rows will go to testing and how many rows will go to the testing mark? When it is 60, 40. Okay, tell me when it is 80, 20. Okay, don't get confused. If I am having 100 rows of data here, okay, 100 rows of data, okay. So if I want to split my training as 60-40, so how many rows will go for training and how many rows will go for testing? Am I right? 60 rows for training and testing 40 rows. If I'm going to split my training testing is a 70-30, how many rows will be going for training? 70 rows. And obviously for testing, you will be having 30 rows. If it is 80-20, training will have 80 rows and testing will have 20 rows. Okay. So can you able to understand how naive Bayes is functioning now? Are you clear with these things?
Yes, sir.
Okay. So like this, we have to calculate all the possible days and given conditions. Okay. So with each and every probability like this, it will take each and every probability in the given table. So we have taken only one condition, day is equal to holiday. Then again, we have to take day is equal to holiday, discount is equal to no, free delivery is equal to no. Like that, it will calculate another probability. Then next, it will take day is equal to holiday, discount is equal to yes, free delivery is equal to no. Like that, it has to calculate another probability. So based on the probability it has analyzed from the condition probability, when I'm giving a new data, it will give the correct outputs. Okay. Are you clear? Are you clear with these things? Shall we go to the hands-on session?
Yes, sir. Yes, sir. Fine. Okay.
So before going to the hands-on session, we can see some of the evaluation metrics what we are going to use for these hands-on session. Okay. So we are going to evaluate it using the metrics confusion matrix. You might have heard these things in your earlier sessions. If not, I will tell you what is so this matrix. Okay. So from when I calculate the confusion matrix, we will get all the values. So we can calculate the accuracy, the sensitivity, specificity, and precision, negative prediction value. All the things we can calculate from the confusion matrix table. Okay. So how it's going to predict this confusion matrix in sense? So here positive and negative. Here what is our condition? Yes or no? Am I right? Purchase product yes and product no. Same way, we have to give what we are going to predict, that we have to give here. So yes or no, here also yes or no, by yes or no, by yes or no. Okay. And true, positive, and sense. So it will be, we are giving two data, am I right? Training and testing data. Okay. So I'll give you an example. See here. Actually, this is the predicted values. In the predicted value sense, whatever values for test data, that will be here. By yes or no in test data, this is actual values which we have trained. Okay. So by yes and no. So what is the predict value? See, first condition is true, positive. So you are pregnant, you should say, right? So if it is pregnant and those it is predicted correctly, you are pregnant, that is called as true positive. And here false positive in sense, see, really you are pregnant, but you are not pregnant, but it is telling that you are pregnant. This is false positive. If it is false negative, the person is predicted as, it is predicted as not pregnant, but actually the person is pregnant. Am I right? That is false negative. And true negative in sense, what you are going to say, you are not pregnant, and it is telling that you are not pregnant. So these two are correct. So if you are pregnant, it is telling it is pregnant. If you are not pregnant, it is telling it is not pregnant. These two are correct data. And if I am seeing this, the person is not pregnant, but it is telling that the prediction is telling that it is they are pregnant. Same way here. See, the person is, they may type not pregnant. The person is actually pregnant, but it is predicting that you are not pregnant. That is called as false negative. So there are two types of error we can calculate from the confusion matrix. One is type 1, which is false positive, and type 2 error, which is false negative. So from this, we can predict this. Okay. So here they have given the formula how to predict this. Sensitivity is in, it is called as recall. So whenever we are going for classification, where accuracy where a measure of performance is based on this confusion matrix. One is we are going to predict sensitivity, that is recall, precision, then accuracy. From this accuracy, we can calculate F1 score. Okay. So these are the major metrics which we are using for classifications. So if I want to calculate recall, what is the formula? True positive means this is the true positive data divided by true positive plus false negative. This will give the recall value. Okay. Then specificity means true negative. So we are going to calculate true negative divided by true negative by false positive. Okay. Then same way, precision, how we are calculating from these column. First column, we are calculating precision. True positive divided by true positive plus false positive. So precision and recall is very, very important. So this is recall and this is precision. So this is negative prediction means we are going to take true negative and divided by false negative and true negative. If I want the accuracy of overall thing, what is the formula for calculating accuracy? True positive and true negative. This is the correctly predicted data. Am I right? True positive. If you are pregnant, it is saying pregnant. If you are not pregnant, it is saying it is not pregnant. So this is the correct data. So true positive plus true negative divided by all the values. True positive, false negative, false positive, and true negative. This will give the overall accuracy. Okay. If I want to know the F1 score, see F1 score in sense precision and recall. We are going to find the precision and recall divided by, so that I will tell you in the hands-on session how we are calculating F1 score. Okay. So obviously we have to know the F1 score. This will give the very accurate result among these all. So if we want to know the F1 score, obviously we need to calculate precision, recall, and all these things. Okay. So next, see, this is the thing I have given you in the slide. You can later refer it. Okay, how it is calculating. So see, in the true positive, it is having 9, and in the true negative, it is telling 2. So what is the thing? True positive, green color circle is identified as green color circle, but 2 circle which is green is identified as green. So it is labeled negative. Am I right? So from this I have to calculate. So if I want to calculate these things, see how we are going to calculate precision. 9 true divided by 9 plus 2, 11. So it will give the precision value 0.81. Same way, if I want to recall, the recall means true positive. So true positive divided by the column value, true positive plus false negative. So this will give the recall value. F1 means 2 into precision into recall divided by precision plus recall. So this will give the correct measure of your model. Okay. Among this, F1 should be calculated. If I want F1, we need to calculate precision and recall. What is the formula for precision? That is nothing but true positive divided by true positive plus false negative, and for recall, true positive divided by true positive by plus false negative. So all these things are given in the table. Okay. The next, we can also measure it using cross validation. Cross validation in sense, we are going to define the test data randomly. See, first, this is k is equal to 5. When k is equal to 5, 5-fold cross validation because 5 data set is taking randomly. So 5, first this 5 will be taken as test data, remaining will be taken as train data. Then again, see, it will take next 5 data as test and the remaining thing is training. Then third 5 is test data, the remaining thing is trained until it complete the full data. It will split the data like this. So first 5, second 5 will training like this. If I'm doing this is called as cross validation. So this will validate your score very much, right? So if you are using cross validation also in our program, it will produce a very good result. Okay. So that's all about your session, and we can go to the hands-on session now. So have you tried with the Google Colab, ma? Have you tried with Google Colab? Wait a minute.
We do not have idea about that, sir.
Okay, I'll tell you. I'll tell you. You just go to the Google Colab, go to Google and give Google Colab. Okay. So if not, if we are not using Google Colab, then we have to install Anaconda or some other Python installation we need to do. If you are using Google Colab, you don't want to do any installation directly, we can go for our code. Okay. Just go to Google and give Google Colab. This is Google Colaboratory. Okay. So you can do your Python coding in this Google Colaboratory itself. Okay. So just go to Google Colab. You will get a first option Google Colab. Okay. So once you click on this, you will get like this. So you have to log in with the help of your email ID. Okay. So I have already used this. I have logged in. So it is showing directly going to this page. Can anyone try it and you can tell me what you are getting? Just go to Google and you give Google Colab, C-O-L-A-B. I will type in the chat box. Sorry, I'm not getting the chat box. I don't know why. Okay, type as it is. I'm showing it is shown in the screen, am I right? So Google Colab, okay, or you can give Colaboratory. Both the things, Google Colaboratory or Google Colab. So you can click on the first link. Can you tell me what you are getting when you are clicking? So I need to post the link also for this. I'm not getting the chat box. Yes, can you able to see it? What I'm doing?
Yes, sir. We are able to see that.
Okay. So just if you want to work along with me, you just go to Google site and you can give Google Colab. When you give this, you have to log in with your credentials, Gmail credentials like that. Okay. So once you log in, you can go to this file. Okay. You can go to this file and you can give upload notebook or open notebook. Anything is there. If you give upload open book notebook, you will get this. Okay. Or you can directly create a notebook. If you give a new notebook, it will create a new notebook. Okay. So Jupyter notebook, it will be creating. So in that, you can type your Python code directly. Okay. You will get this page. So here you can type your code. So already I'm having some notebook. So I am going to upload that notebook. With that, I can explain it easily because that we are running out of time, I think so. So first, I'm going to choose the file. Okay. So uploading means once you click on upload, it will ask you to choose the file. So I'm going to choose it. Workshop name base. Here I'm having name base this file. Okay. So I'm going to upload this file. Okay. So already we have coded everything. Okay. I will explain each and every line in the code. Then you can understand what is there. Okay. So there are several inbuilt libraries for machine learning in Python. So Python and R is very useful for building machine learning models. Okay. So in recent days, Python is hiking like anything. So we can do anything with Python packages. There are several inbuilt packages in Python to do all the machine learning models and deep learning models. Okay. So first we have to import, like in C language, you will be importing your other files, am I right? Like this, we need to import the packages. So these NumPy is nothing but this is the package which
Sir,
is
Rashekar, sir.
called Python. Yes, sir.
Sorry for interruption. Can you please check the chat box now, whether it is open to you?
Chat box. Okay, I'll check it, sir. No, sir, I cannot access the chat box.
Okay. Fine, sir. You continue, sir. We will try to resolve
Okay.
this, or else you can
Okay, sir.
share to us. We'll share to the participants.
Okay, sir. So first I will tell them how to do. Later I will share all this file and they can work out, sir.
Fine, fine. Thank you, sir.
Okay, sir. Okay. So this NumPy is nothing but one of the packages which we are going to use for machine learning. So this NumPy full form is numerical Python. So obviously we will be using it for array objects. Okay. If you are going to use any array objects, we will be using this packages. So we need to import the package. So the way of importing the package is import NumPy as NP. So we are renaming this NumPy. So we have to use this NumPy keyword often. So I'm renaming NumPy to NP. So this is the as means this is the alias name for your NumPy package. Okay. So whenever you want to use NumPy, instead of NumPy, you can use NP. Okay. Then another package we need to import pandas. So this is nothing but data frame. So we are this is also open source library to build a NumPy library. So it is built over NumPy library. What is NumPy library? It is used mainly for array objects. Over this array objects, we are having data frames. So this is mainly used for data frames. So I will show you what do you mean by data frames. So it will give a table model, okay, rows and columns model. The data can be arranged in rows and columns model with the help of data frame structures. So for that, we are importing this package, import pandas. So same way, I'm renaming this pandas as PD. Okay, these are the standard ways for naming. So you can use any names instead of PD. You can just give P or anything. But these are standard names. Okay, so they are so that I'm using it. Okay, then we are going to use naive Bayes algorithm. Am I right? So there is a separate package called scikit-learn, or we can call this as sklearn. Okay, so this is also one of the package scikit-learn. So where this package contains all the algorithms related to your machine learning. So this is one of the algorithm in supervised learning. Under classification, we are having naive Bayes. So the name of the naive Bayes algorithm is Gaussian NB. So NB is nothing but naive Bayes. Okay. So this is the name they have given. If I want to use this algorithm, I want to import the package scikit-learn. Am I right? So scikit-learn also be called as sklearn. So from sklearn, okay, dot naive Bayes. So we are going to import this specific algorithm. So dot naive Bayes, import that algorithm name. So this is the algorithm name Gaussian NB. Are you clear? So these are the things we are doing before starting our coding. So we need to import these NumPy packages, pandas, and sklearn. Sklearn is mainly used for importing this algorithm into your coding. Okay. Then I have told you already what are the performance measure we are going to analyze it. So that also can be, it is available in the package scikit-learn. So from sklearn dot metrics. So what are the metrics, performance metrics we are going to use? So we need to use measure the accuracy score, then classification report we need, then confusion matrix. I have told you what is confusion matrix. So only from the confusion matrix, I can get accuracy score, right? Then we will get the entire classification report. I will show you how we are getting that. Okay. Then we need to import this. Okay. I have told you we are going to use cross validation. If we are using cross validation, automatically all the data can be used as a training as well as testing. Okay. That is the purpose of cross validation. And next we need to split our data, train test split. Okay. That is also available with the package sklan. Okay. And for this training test and split, we need to give dot model selection. So we are going to build the model using naive Bayes. So sklan dot model selection import. What are the things we are going to import? So we are going to apply cross validation function. So I'm giving this as cross valid score, then train test split. This is for splitting the training and testing data. Okay. And this is for what are the performance we are going to measure: accuracy score, classification report, and confusion metrics. So for that, we are giving dot metrics. Okay. Are you clear with these two lines? Two cells. Here, see, you can run here. If I click this, it will run. So if there is any error, it will show or it will run completely. So each and everything, what I'm typing, this box is called a cell. Okay. So we can run each and every cell separately, or we can run it as a whole. So here there is an option called, here there is an option to run. Wait. Yeah. Run all. Okay. Run all means it will run all the cells simultaneously. But if you are using like this, we can run individual cells. So here given as a tick. Am I right? You can see a green color ticket. There is no error. Just I have imported the packages, and here I have imported some other packages which we are using for metrics measure and for train test splitting packages I have imported. So if I run this again, it will get tick. So there is no error. Then we are going to use the data. Am I right? So this data, how we are going to use it? So this is the link for using our data. So copy selection. So if text chat box is available, I will show you. So still it is not available. So I will show you in the, see, I'm copying this link and I'm going to paste it here. Then you can see the data. See what we are going to find in our data. See, we are going to find whether the patient is having diabetes or not. Okay. So if it is 0, the patient is negative diabetes, and 1 is it is positive, diabetes is positive. So what they have given us input data, glucose and blood pressure. Using these two input data, we are going to predict whether the patient is having diabetes or not. So this is our input data. So normally we'll be having some 300 rows, I think so. I don't know exactly. So there are some large set of data. So this is the data set which we are going to use. Okay. So coming here. Okay, so I have to read this data, okay, in a read CSV format. CSV format is nothing but in an Excel, that is a rows and column. It's comma separated value. CSV is nothing but comma separated value. So we are going to read this. I have told you PD. So for reading the data in rows and column, I have told you we need the package pandas. That is, so for that PD, so that pandas dot read CSV is the keyword. Read CSV means we are going to read these data, input data in the form of rows and columns. So that can be done only with the help of the package pandas. Okay, so that is the thing. And I'm assigning those data to the variable data. Okay, then I have to check whether we have got the data in this variable. So for that, in order to check this, so I'm running this. So now the data has been assigned to the variable data. So these data, so whatever data we have seen, it will be assigned to the data. So now I'm going to display those data. So data dot head of 10. If I give head of 10, first 10 rows of the table will be displayed. So data dot 10 head of 10. So it is going to display first 10 values. The data see 0 to 9. So if I run this, you will get the data. See 0, 40, 85, 0. Here also you can see 40, 85, 0, 40, 92, 0. So first 10 values, it is 40, 92, 0. So all the data are being assigned to variable data. So how we are assigning? Using pandas.read CSV. Okay. So next, what is the next thing? See, we are going to in this data, we are having diabetes. But what is our aim? We need to predict whether the patient is having diabetes or not. So we have to remove this column from the table. Am I right? So this has to be identified by the naive Bayes algorithm. So we are going to remove these column. So in order to remove this column, what I'm giving data. So data where my data is present dot drop. So drop will drop this particular column. So which column I need to drop? That is the thing I have given in the single quotes, diabetes column. So this name should be as it is here. If you are missing anything, it will say there is no such columns found. Okay, comma axis is equal to 1. What do you mean by axis is equal to 1? So whether I want to remove, yes, I need to remove this axis. So I'm setting axis is equal to 1 here. Okay, I'm taking this data and I'm assigning it to another variable y. So x will have only this glucose and blood pressure now. So in the x data, see, again, if you want, I will show you. So after running the C. Now, can you understand these two lines, X and Y? In the X, what data will be there? Only glucose and blood pressure will be there. And in Y, we will be having diabetes alone. These data will be alone there in the Y. Okay. So I'm running this. So it is run C. Then I'm splitting my data. Train, test, Y train and Y test. See, train is nothing but this is the train data. Okay. So in the train data, you will have this glucose and blood pressure. Okay. And in Y train, what you will be having? You will be having this column alone. So in whatever Y, that will be here. Okay. Y column is having only diabetes. So training, if I take training, I need all the things. This glucose and blood pressure I need, that is in train data. And diabetes is Y train. So whatever data that is present in train, the corresponding diabetes data will be present in Y train. Same way test. So test will have those data that are not in training, and Y test will have these columns alone. Okay. So we are going to split the data like this. Okay. We have to split the data under training and testing. So what we are using, see train test split. So for importing these function, we are importing a package with the help of sklearn model selection train split. If you are not, if you fail to import this package, then at this point it will throw an error. Okay. So train test split x comma y comma test size is equal to 0.25 given. 25 means so test size will be 25% and train size will be 75%. So it will divide like that. Okay. So if there are 100 rows, 75 rows will be for training and 25 rows will be for testing. So it will split the data automatically from the given inputs. So for these things. Okay. So random state means we are giving some random value. So based on this random value, it will automatically split the train and test data. Okay. So next we have to create a model. Okay. So what we are in the model, what we are going to do, see. So we have defined the distance plane. Now we can call the function model is equal to Gaussian naive Bayes. Okay. So this Gaussian naive Bayes is the algorithm which we are going to calculate. Right. So after calling this function, I need to fit it. So model fit is equal to what are the things I'm passing as a, so this is the function, right? I'm calling a function. Model fit is a function. So this is the function definition. If I want to write anything in Python as a function, so this is the keyword. Diff is the function keyword, and this is the function name and the parameters of the function. Okay. So here I am calling the function model fit, model comma train comma test comma y train. So I will show you what is there. I will create a new cell. Okay. So here you can see x. So if I give x, see only glucose and blood pressure is there in the x. I have told you here, am I right? Same way, if you want to display y, okay. If I give y, only this diabetes columns will be there in y. Okay. See, only diabetes 0, 0, 1. So this is the number of total data we are having is 995 data we are having. Okay. We have not we have split it train and test. So if I want to know train, okay, train. So if I display train, so you can see what is there in train. See, train will have some random data. See, it is taking 618, 499, 404. In those rows, it has taken. So totally 995 rows are there. So it is taking the rows randomly and assigning it to training. Okay. If I give train y underscore train, so that will have the corresponding same values will be 618, 499, 404. You can see that. So what is there in train y train? So if I display y train, y train, you can display that. And if I run the cell, see same rows. So you can see 618, 499, 404. Same here, 618, 499, 404. The corresponding diabetes column of this train will be there. Are you clear now what is there in the data, how we are splitting it? Same way, test will have this glucose and blood pressure, which is not in training, and Y test will have only diabetes column, which is not in training. Are you clear? So likewise, we have splitted the data. Then we called the function. Okay, we have called the naive Bayes algorithm, and we are passing this algorithm through this function. So what are the things I'm passing as parameter in the algorithm in this function? Model fit. First, we are going to ask the algorithm. What is the model? So to the model, I have assigned the algorithm Gaussian naive Bayes. So first, this algorithm will be passed as a parameter. Then I'm passing train data, then test data, then Y train and Y test. We are passing these as a parameter. So what is there in the train data? So it will have only glucose and blood pressure. And test, it will also have only glucose and blood pressure. And train, Y train will have only the diabetes column of train data, and Y test will have only the diabetes column of test data. Okay. So this I'm passing here as a function. So this is the function definition. So in the algorithm, naive Bayes will be copied, and in the train data will be copied, in the test data will be copied, and Y train means diabetes column of train data will be copied, and Y test diabetes column of Y test will be copied. Okay. Then if CV is equal to, we are defining another variable CV. So this is a variable is equal to true. I am setting is true. Then I have told you we are using cross-fold validation. Am I right? Cross-fold validation since we are giving it is equal to 5. So from the data, first 5 will be considered as test and remaining will be considered as training. Like this it will take. So we are using cross validation also. So CV fold is nothing but cross validation. If CV is equal to true means if cross validation is equal to true, so that is the thing we are checking. So already we have passed CV is equal to true. So if CV will be always true, so it will execute this. So we need to calculate the cross validation score. So what we are calculating, we are passing algorithm, train data, test data, and cross validation fold is nothing but 5. So CV is equal to CV fold. So already we have passed CV fold is equal to 5. Then scoring is equal to, we are using F1 score. Am I right? F1 macro. I have told you what measure we are going to use. F1 macro. Okay, F1 score. Then we are going to predict the testing data. So how we are going to predict the testing data? Algorithm. So what is the algorithm? That is Gaussian naive Bayes dot predict. So predict means we are going to predict the test data. So test, we are going to pass the test. That is training. This is the testing data, right? This testing data will have only glucose and blood pressure. Okay. So from this, it has to predict what is the corresponding Y train. Okay, what is the corresponding Y train? Okay. Are you clear? So now this train data, test data will be predicted, and I'm printing the model report. So model report is classification report. I have imported the classification report. Am I right? So in the classification report, I'm passing two data. So Y test means this is we have defined. We have splitted Y test. What is the data in Y test? So what is there in the Y test mark? The corresponding diabetics column of testing data will be there. So that is the Y test. And what are the predicted value? We have predicted the test value. So it will give some data based on the naive Bayes probability, condition probability. So Y test data and the predicted data we are comparing, and we are generating the classification report. So in the classification report, see what are the things I'm printing. So mean of CV score I'm printing, mean of standard deviation of the CV score, validation score I'm printing, all these things. Then we are going to get the confusion matrix also. So confusion matrix, what are the parameters that we're passing? Same way. Test data, Y test data, and predicted data has to be followed. Okay, so it will give the data. See, the precision, recall, F1 score support. So whatever things we are calling here, see in the classification report, all the things we will get. We will get precision, recall, F1 score, and support. So from the predicted data, see what is the precision and recall F1 score? We are getting 94 accuracy, 94% accuracy. Okay. So it is most probably predicting 94% correctly. Remaining 6%, 0.06 is okay. That is error rate. Are you clear? If I run this, you can check this. So up to this we have run. I am running it. So this is okay. And I'm running this model. See how it will predict everything. See, just providing 94% F1 score. Precision is 95. What is precision? True positive divided by true positive plus false positive. Recall means True positive divided by true positive plus false positive. That is the thing. Okay. Then accuracy, overall it is getting 94%. Accuracy means true positive plus true negative divided by all the combination of confusion matrix. Then whatever the mean average score is 93%, deviation is 0.02. Okay. So this is the overall report, CV report we are getting. Okay. So among this thing, see, correctly predicted 121 data are correctly predicted and 113 is correctly predicted as negative and 121 data are correctly predicted as positive. Here what we are getting, false positive means 9 data which is diabetes are predicted wrongly, not diabetics, and 6 patient which is not having diabetes are predicted as diabetics here. That is the thing. This is the CV report. Are you clear with these things? Are you clear? Guys, are you clear? So that's all about today's session. If you have any doubts, you can ask me. So I will share all these materials, PPT as well as this notebook to the organizers. They will share you. Thank you. Thank you from my part. If you have doubts, you can ask me.
Sir, thank you for that wonderful session, sir. It is very productive as well as interesting to all. Now, participants, if you have any doubts or any queries, you can ask resource person.
Sir, if there is no queries, shall we wind up the session?
Yes, sir. Sir, once again, thanks for the wonderful session, sir. We'll meet you soon
Okay,
some other
thank you,
time
sir.
at some point. Okay, sir.
Thank you so much. Thank you, participants, for your patience.
Okay, sir. Thank you, sir. Bye, sir. Dear participants, the next session will be started within 10 minutes. I hope you people please be connected with it. The next session will be started within 10 minutes. There is an unexpected delay from the resource person. He said he will be joining in 10 minutes.
Magesh, sir.
Yes, sir, please.
Sir, where could I share these materials, sir?
Sir,
Shall I
I will
mail you?
contact you, sir. Yeah, I will
Okay,
contact
okay,
you.
okay.
Then I will let it be shared with the participants, sir.
Okay, sir. Thank you, sir. Thank you
Okay,
so
sir.
much.
Hi, Siddharth here.
Hi, sir. Just give me a minute.
Okay, so this is a AM modulation. Okay, there are only okay. So you see this one, and you see this. There are four blocks. So this one is a modulation block. Okay, this is an AM modulator. This one is a AM demodulator block. And here we have a carrier signal, and here we have a message signal. Audio AM signal means audio frequency. Audio frequency means what? The message. Okay, so you can create your own carrier and message signal here itself. No need to go anywhere else. Okay, so this is a modulator. There are two inputs. For the modulator, there are two input signals. One input is your audio frequency signal, AM signal. Okay, the signal you want to modulate, the signal you want to transmit. Okay, so take a wire, and the wire will be there. Okay, connect the wire will be there. Connect AM
This
signal.
wire you need to use. You should not use normal wires. These type of wires, it will be there on your table. You are going to connect these wires.
So take this one like this. Okay. We have to connect the AM. Okay, similarly for the carrier signal, so take a
Okay, good afternoon, everyone.
connector.
Sir, Siddharth sir, welcome to the short-term program titled Emerging Topics on Electronics, Instrumentation and Communications. Hello, sir, is my voice audible to you?
Yes, yes, Mahesh. Thank you.
So, dear participants, I introduce Dr. Siddharth Chauras here, who is a data science and machine learning enthusiast, practitioner and researcher. He has received PhD in computer science, with AI being his field of research, and is currently working as a senior scientist in TCS. Out of total 17 years in IT, he has been in the world of data science and AI since 8 years. It is difficult to find a field where AI is not intervened to provide cutting-edge solutions. He is really fascinated by the outreach of this field of data science in varied real-world domains like electronics, communications, telecom, healthcare, finance, etc. He has driven projects across multiple domains to generate and create value from data. So it's my warm welcome to introduce Dr. Siddharth Chauras here. Sir, now you can take over the session and you can take over the session, sir.
Yep. Thanks, Mahesh, for the introduction. I'm going to share my screen. Can you please confirm if you can see?
Yeah, please.
So now we have to do this thing for three cases. One is n is less than 1, n equal to
This is
Sir,
visible.
again, sir, excuse me, the background sound is coming, sir, from your
Yeah.
side.
From my side, sir.
Yes, sir, yes, sir. The class is taking someone is taking class.
Okay, fine. I will just mute my mic so that it will be fine, sir.
So hope my screen is visible now.
Yeah, it's perfectly visible, sir. You can carry on, sir.
Yes, thank you. Yeah, thank you. Now this is quiet and nice and quiet. Okay, so good afternoon, everyone, and Mahesh sir already introduced me. And today we will be going to talk about ubiquitous AI, AI which is present everywhere, and how the AI from cloud to move to edge and now moving towards the tiny ML and all. So that's where we'll be talking and we'll be focusing our energy. So we'll be not seeing any code, rather we'll be talking about the cutting edge domain, cutting edge field of AI, which is very intervened, very mingled with the branch you are working in, that is electronics. And that is where we'll be looking at today. But before that, we'll be covering few things. So first agenda is going to be AI terminology that we'll be using. So I already saw that you already have covered 2 AI based sessions. So I'll consider a few of them are already you are already familiar with, but still I would reiterate so that if anybody is left off or anyway, if you have any questions. So I'll be reiterating few terminologies that we'll be using in the session. And then we'll be looking at what is the current state, where the research till now has taken us to, and where the new areas, new avenues are coming through. Okay, and you'll be glad to see how new AI-based revolution, or you can say fifth revolution, is going to be very dependent on electronics and integrated circuits and all. And that's where the entire focus is going to be going forward. That is what experts are seeing and envisioning, and that we'll be talking more. We'll be seeing how cloud ML, or that is cloud AI or edge AI, or even tiny AI is going to be related, or what do you mean by that? And finally, we'll be looking at what are different tech enablers. What are the enablers that will be required to actually move from cloud to tiny ML and all. Okay. Also, we'll be looking at few challenges. Initially, challenges of the cloud that we are seeing. What is the requirement? Why the requirement is to move to edge, and then why we are moving ahead towards the tiny ML, tiny AI. Okay. So moving on to the first terminology section. So AI versus machine learning versus deep learning, and that is what I'm not sure how many you are already aware of, but what is artificial intelligence is any technique that enables computer to mimic human behavior. And that was the envision when they coined the term artificial intelligence. Initially, they were trying to mimic human being entirely. And soon they found that, yes, it is not that easy to do that. And that was the vision that came in 1950s and all. And then actually there was an AI winter where most of the progress got stalled, and then it again came in, it again started progressing once we started looking at machine learning. And machine learning was something that where we were focusing on very specific problems which very specific problem in terms of domain, very specific problem in terms of problem statement itself. For example, if our data is belonging from financial domain, we are going to build something which is going to be intelligent, but will be capable enough to dealing with that particular data set or particular domain itself, not as if like it can mimic human being, which is capable of tackling multiple things, multiple domains in at once. Okay, and then finally there came in deep learning, which is again can consider a subset of machine learning, which is all being focused upon neural network. And when we say deep neural network or deep learning, it means the neural network we are talking about is going to be deep neural networks. That is more than one hidden layer is by definition called as deep network. Okay, so all those innovations, all those AI driven technology advancements that we are seeing today is because that what makes it. We all know Alexa, we all know other Cortana. They all are AI enabled bots. They are all AI enabled NLP engines, which respond to your voice. There can be multiple vision based applications which we can see, for example, using our face to unlock our mobile phones. So all these technology advancements are happening because of deep learning. Okay, so we'll be focusing more on the deep learning area, and because that is where the current state of the art is. In another view of how AI and ML technology are actually they align together. Artificial intelligence kind of superset of everything. Machine learning, when we are talking about getting information, getting learning itself derived from data. Okay, and then deep learning, which is again a sub part of machine learning, but instead of all varied kind of algorithms that can go in, we are going to focus upon neural networks, and that too deep neural networks. And another deep neural networks, so algorithms like CNNs, that is convolutional neural network, recurrent neural networks, and more recently transformers and all. These are coming from the deep learning world, And that is what driving the current innovation or current outreach of AI-based applications. Okay, few additional terms. I have used cloud, edge, and tiny AI or tiny ML. So will be talking about that also. Okay, when we say cloud ML or cloud AI, it means all the processing is being done at some data center or some big processing organization, right? When we say edge, edge is like taking away the processing from cloud and moving nearer to where it is being used. It can be on your mobile phone, it can be on your data center or a machine or a laptop which is sitting near to you, or it can be on some server which is again co-located or at least at some near location, not sitting at say Google data center or IBM data center or somewhere else. So that is where how the cloud and edge are processing. Okay, cloud processing is done in data centers, data farms, edge on local devices. Plus, we are again going to see few more terms. For example, types of machine learning. We are going to only talk about supervised machine learning because most of the business use case, and that was a statement given by Professor Andrew Ang, who was kind of innovator or an initial a paramount or a very important personality in the world of AI. And he stated that 99% of the business value, I'm saying business value, is being derived or being provided by supervised learning only. And when we say supervised learning, it is like we have lot of data which is labeled. That is, we know that what is the true answer for that along with the data. And we learn based on that as if we are teaching our baby. For example, if you do this, you will be rewarded. So you'll start recognizing apples, recognizing orange, and say after 5 or 7 times. So that's how we train in case of supervised learning. And that too, we have different stages of that. We have training, we have inference. And finally, what we get is a model. And what is actually a model? It is nothing but a mathematical approximation. It is some very complex mathematical function which is good at mapping input and to outputs. Okay, so few terminologies here. Now let's look at how we have progressed in say last decade, and then we'll see what are the challenges that we are seeing, which is while we are moving to the next say 2020s and 2020 next decade again, next another one. Okay. So if you can focus on this, I'll get in a pen. So if you focus on these 2 years, you can see this data is for ImageNet dataset. ImageNet is a very popular dataset for image recognition, and it contains say 14 million images, around 14 million images with 1 million labeled information and with 21,000 classes. So that is a big data set, which is normally used as to gauge in how good your performance of a model, how good your model is performing. So most of these statistics that I'm sharing, that is on ImageNet dataset, which is in fact annual challenge is played every year, and this data is for these years. So 2010, 2011, the accuracy or the classification error was at 28 and 26%, and this was kind of stagnant there, right? A very minute change even prior to that, prior to 2010 all. And suddenly in 2012, it dropped by 16 to 16%. That is 10% improvement was achieved in one single year. And what happened there? You see this 8 layers, that is what it happened. And that was the time from where deep learning actually flew off. So before that, they were mostly shallow models. From 2012, AlexNet came. It was presented from University of Toronto by Alex and one more researcher there, and they designed a neural network of 8 layers to identify those 21,000 classes of images, and they instantaneously got the improvement of 10%. And then that brought in a big revolution in the world of computer vision. So from there on, we started moving to heavier layers or heavier models again. So ZF was few improvements. Still, it was at 8 layers. and then 19, then 22, and more recently 152 layers, and there is what to say after that. Okay, so the layers kind of went ballistic. Okay, so what restricted them before this? Why the layers were not used before? First was the computational power, the data, the internet speed, and all those restrictions. So that was got over, and we have big data farms, we have good processing units and all. Plus, the idea was always there, and there was one person who was ready to implement that with all those resources. So that actually created the deep learning revolution, and deep learning flew off after that. And after 2015, 16, the same stage came in for NLP tasks, where natural language processing was got revolutionized. And in fact, in 2016 or 17, there were models which were created which had around, say, billions of parameters, and they were very huge models, was trained on data set like Wikipedia, entire Wikipedia, and those models were trained for, say, months of time. But finally, they were able to achieve those accuracies. Okay, now the error rate is stabilized around 3% or so. So I'm telling about this history because we'll be looking at the limitation of what this deep learning has brought in, and why we have to move to edge, and why we are moving towards a tiny AI. Okay. Now, before that, what is a neural network? And this is how it looks like. I have been talking about what are the number of layers, how many neurons or how many parameters are there. So this is what it shows it. So we have inputs, right? This is number of features. It can be anything. For image, it can be number of pixel, or what is the pixel size, pixel density of your image. For languages, it can be number of words, or whatever your feature representation is giving, and so on. So these many inputs. In short, these are a number of inputs, and these are going to be number of layers. So right now, this is a deep neural network because there are two hidden layers. This is H1 and this is H2. Okay, two hidden layers. That's why it is deep neural network. So anywhere where more than one hidden layer is used, the term will be used as um, deep neural network. But really, factually, all the neural networks which are being used currently, they are having more than 100 layers. And to train such a network, we really require GPUs, and not only GPUs, we require powerful GPUs and maybe multiple GPUs altogether. Well, because the data set we are training, they are also going to be very large. Okay. So as of now, for the research, as we see, we were making good progress. We improved our accuracies from, say, 70, 75%, 78% to 85%, 86, 10%, or even much more. Now, recently, it was established around 3% error, that is 97, 98% accuracy. Right? But what problem it brought in? It brought in the problem of scale. It brought in the problem of resources. It brought in the problem of uh, uh, who can use actually. Okay. Now, again, before moving on finally to all the limitations, let's say right now we said that it was 21,000 classes. What do I mean by that? What do I mean by training? What do I mean by inferencing? That's all. I'm considering that you do not know anything. That's where I'm moving on and trying to take you to the current cutting edge. So training is once when we are teaching our model to identify whatever we want to teach it. For example, in this particular case, cats, if I'm training a model which needs to identify cats, so not one image, not two image may not be sufficient enough. Images with different types of cats, images with some cats, some not cats, images with different angles of cats. These kind of input data will be required for the training purpose, so that our model is able to recognize all the possible combinations when that can exist in the real world. And depending on your training data, how good your training data is, the accuracy of the model will be there. But what happens in training? In the training time, all the data is provided to our model. The data is labeled. That is which one is a cat, which one is not a cat, which one is a dog, which one is a rat, or whatever the other animals are. But it needs to be labeled. Okay, so the training data is fed to our model, and model tries to learn or get trained during that time. Okay. And this training for computer vision for the task that we have discussed till now, it normally takes a good amount of time. I'm not talking about for you to go in and bring in a data set, a small data set, and start working on that, and you say it will take months. No, with current good computational power, it can be done on free GPUs provided by Google within 6 hours or so if your data set is still big enough. But if you are not working with a data set big enough, which is which is having 14 million images with 1 million labeled images. Okay. Now, so your training is done. For example, now your model is able to recognize what is cat, what is a dog, and what is not a cat. Good part is with neural network, it always provides a probability or a confidence level, right? So it says this is an image of the cat, and in the inferencing, it tries to identify. The training is done. Now you give an image and model will try to identify whether this is a cat or this is not a cat. Okay, so that was the purpose of our model. So our model is now trained, and we have moved into the inferencing stage. That is, we are inferencing whether this is a cat or this is not a cat. No more training is required. Model is trained. It is now going to be used for referencing purposes. So it's feed it an image, and it will tell whether this is a cat and with what confidence level or with what probability it is going to it is recognizing that is a cat. Okay. Similarly for dog and all for other images. Okay, this is called machine learning inferencing or AI inferencing. In short, two phases. Machine learning process have two phases. That is, one is a training phase, another is the inferencing phase. Training phase is once we have when we are using a big amount of data, we are training the model, and then we are testing whether we are okay with that, with the performance of the trained model. Are we good with that? And this process is pretty iterative and really time consuming. And the training phase actually requires big GPUs. The training requires good computational power. So and so on. So training, if it is happening on cloud, that completely makes sense. Okay, but now when we are moving, once the training is done, our model is trained and it now knows to identify whatever it has been trained upon. We move on to the inferencing stage, right? Inferencing phase, where it is now going to be treated as trained. It's something which can give you output based on whatever it has been trained. So feed it an image, it will tell you whether this is a cat or this is not a cat. That's it. Because that is what our model was trained upon. And this is called as inferencing phase. You remember in 1997, Gary Kasparov was beaten by IBM Deep Blue. And that was kind of one of the revolution point where we really thought, yes, computers can do wonders. Okay, and not only that, much later in 2016, even AlphaGo champion was beaten. I was some San or so. He was beaten by AlphaGo program, right? You know, so these kind of programs, which is showing these kind of performances, how they were trained, how much they were trained, and how much resources they consumed. So let me give you a few data. So this, in fact, Google or AlphaGo was the organization which, Google trained this AlphaGo program, and it in fact had to design their own silicon chips, which they called as TPUs now, that is tensor processing units, and they required 5,000 of them in their data centers, and they trained for good amount of time, and during that training process, they consumed more than 30,000 watt of electricity for this training purpose itself, which is huge requirement of resources, right? They definitely have reached astonishing feat that they are overcoming human beings by just program. But what is the amount of resources they are consuming? This is what they have used. They are consuming this machine learning in its current form is very resource intensive, very costly, very I would say it eats away all the resources that you have. And at times we may do not have that many resources. So what are downsides now? First of all, I'm not, or rather we are not that rich that we can have 5,000 of our own processors, that too, which have been custom designed for us to train them or to utilize. Second, it was centralized. We were using data centers which were at one single location, and every data needs to go to those centers. right? So this means anything, any information which is even private or even that needs to be secure had to be sent to those data centers. Okay, which raises a big privacy and security concern. Next is lots of power required, of course, along with just the electricity consumption. We also require a lot of bandwidth consumption as well, bandwidth of internet, and that too is it gives a lot of latency if we are moving into a real world situation where we require response at the almost instantaneously. Plus ethical aspect. By ethical aspect, we mean privacy and security concerns. So these were the downturns. Okay. So now the answer lies in microcontrollers, which you guys are champion for. Microcontrollers or chips or SOCs. So you guys are champion for that, and that is the field that we are moving on. And that's the field where we'll be looking how what is the answer of all this resource intensiveness to we still require the performance, but we have to change our approach so that it can have a better outreach. Okay, so any questions before we move on? I'm not sure, Mahesh sir, how we are doing. We take questions at the end or we take questions in between? Okay, so no response means good thing. I'll be taking all the questions at the end then. So this is a microcontroller. Probably you guys are more familiar with microcontrollers than we are. I'm just a computer science guy who has never actually seen microcontrollers when was in college for apart from one semester. And it's only recently that we have again come across with that. So, but this is a microcontroller which is this is small, 2.7 inch, and with all the brain having in this red red rectangle, and this is pretty efficient, cheap, small, but so these are its pluses, and minuses are going to be it's slow with limited memory. So memory which we were using till now was of gigabytes and terabytes and of any size. Now we are going to we have to work in very constrained environments and yet perform those amazing AI based inferences also. So how we achieve that? By moving to the edge and finally moving to the tiny side. Okay, so how it has been, hope now it makes more sense to you. So till now we have been doing cloud computing, or cloud resources were used for all the training, and all the big deep neural networks were used for training purposes and inferencing and all. So slowly we had to move on to the edge because we simply do not want to. If suppose I'm working on my smart home and to make my home smart, and I just do not want to send all the data which is very personal to me. For example, where how many rooms are there, how many rooms are lighted at a particular time, how many microwave ovens are running at that particular time, how many times I brew coffee from my coffee maker, and so on. So I just do not want to send all my personal details to Google data centers. They need to be private. They need to be residing on inside my home. And that's where the edge comes in. Or another one, and the TinyML comes in, right? So actually, the entire inferencing is still, entire training process still lies here, but the inferencing goes to this place. So the model training, which is more data intensive, where all the training, all the data needs to be required for the training purpose. All the compute will be required to learn around that. So everything happens is still on the cloud. But once that model is trained, the trained model is shipped through FOTA, that is firmware upgrade or something, to your mobile or to different devices which are supposed to run to microcontrollers and all. They are shipped to your let's say mobile device as an example, because that is we all are very familiar with that. So for example, if we are going to make use of say Alexa, Cortana, and anything, we are going to make use of models which are residing inside your mobile. They are not going to communicate to cloud for every single time, because otherwise this without connection things won't work. For example, if you're typing, few things. You get suggestions. What is can be the next word? What are your spell mistakes that you're making? And then auto suggestions comes in. So those things are happening on the edge at your own device with the help of models which have been trained on the cloud, shipped to your mobile phone, and can provide the intelligence then and there. So we are talking from cloud, moving from cloud to the edge. That is what we are talking about. So again, another view. So what happens in the cloud? Training training is of course going to happen always on the cloud, because there we require good training procedure. We require big amount of data to get our models properly trained. We require good compute to get the training process quick and fast, and we require that. So all the training process is still going to happen on the cloud, but in the cloud AI, the inferences also used to happen on the cloud itself. Means all the data information needs to go to the cloud, and there every in the inferences will be derived and sent back. Okay, but what happens in the edge AI? The model is trained. It is shipped to the machine directly on your mobile phone, on your tablet, on your cars, and so on. And inferences happens only there. So this communication is no more required for each and every inferencing or for each and every communication with there, right? So that is the difference between cloud and edge AI. The inferencing now resides on your laptop, on your machine, on your system, and so on. Now, what is the difference? What is the difference it is bringing in? First of all, the latency, plus we may be using mobile phone where there is no internet at all. So that risk is over now. Plus we are secured. We are not sharing all the possible data that needs to be used, that is required to the cloud or sending to some other data centers, which we do not know what they're taking away. So all those data resides on your machine. Plus we are saving a lot of bandwidth. And to give you some idea on how the bandwidth requirement is, so 1 Mbps image and workflow downloading, and this kind of speeds are required for when we are dealing with cloud information. So if we are training or rather doing inferencing on the cloud, and you want to get a image recognition for a person, whether this person is who, so an image needs to go to the cloud. Inferencing will be done on the cloud and come back. While the same thing can be done with the trained model sitting on your mobile phone or sitting on your SOC, that can be done at their end. So we get away with all this bandwidth cost, with all this dependency on the internet, which needs to be there at all times. Okay. So now we have been talking about edge AI till now. So edge, I think by now you should be aware, or you must be knowing that edge means it can be on your mobile phone. It can be a laptop which is near to you. It can be a server which is near to you, not sending everything on to the Google data centers or IBM data centers or some other data center. So we are not sending everything. So data center part is cloud. Then edge comes in where we have near shore or near to your place, some servers, so that entire thing can be fast paced. While when we are talking about tiny ML, it means actually taking away the AI to those microcontrollers which can be embedded into small things. For example, your washing machine, for example, your geyser, for example, your microwave. So everything can have a small sensor which is embedded into your apparatus, into your appliance, and having a small chip which can provide the intelligence also. And that's where the tiny ML is taking us. So another view, what is IoT device? IoT, you are more aware than me. Cloud is what we have been talking about. So AI on cloud computing, everything happens on the cloud. Your so if you are getting in data from your IoT device, data is sent to a gateway, that is some large amount of data, high data rate and all, that is sent to the cloud. Entire processing happens on the cloud and sent back. Okay, so it's just another view telling that that heavy and expensive computation will be done on the cloud, and it will bandwidth will be used to send to and fro the data that is that we are processing. While but this may not be feasible. Why? Because the use cases, the real world use cases that we are dealing with, they are more near to us, near to us as a person, near to us, to our places, near to our devices, and it really do not make sense to send every bit of data to the some data center which we may not be aware of. For example, these are say some very popular use cases: voice and face recognition. Your mobile phone opens after seeing your face. Maybe it can open after hearing your voice, right? Your disease symptom detection. Like there can be, in fact, there are few smart dresses, smart aprons are being made for patients, so which have sensors inbuilt, which can tell you whether what is the patient's heart rate, what is the patient's BP at all times, which can keep monitoring on that aspects. So these kind of innovations are happening all the time, right? Predictive maintenance, for example, in case of manufacturing, if you are or a big data center which is running, or your machine which is running a particular operating system and generating some logs. So your sensor can sit there and keep monitoring those logs and give us notice that, okay, something is wrong that is about to happen. Handwriting recognition. So these are very popular use cases, and they are more near to us than to a data center, right? So that is the reason why we need to bring AI, why we need to bring intelligence to near to our device than on simply sitting on the data centers. So what is going to happen now? Inferencing will be taken to the IoT device or some near edge or tiny device again. So low power consumptions and a small amount of data. So we do not need to send every bit of it. We may send whenever the connectivity is available. For example, whatever language assistance that we are using on our mobile phone, it will provide the assistance to you, and you may be using those assistants or neglecting those assistants that is or suggestions that are being provided by your mobile phone. So this kind of statistics will be gathered and sent to the cloud for further improvement of their models. But for your referencing purpose, the inference will be provided immediately on your mobile phone from your mobile phone without talking to the cloud, right? So we are still providing the feedback which is required for the improvement of the AI algorithms. At the same time, we are not sending every bit of the data which may not be relevant for the model training purposes. Okay. So I think this may not be needed now. We have already covered. So what we are actually achieving? We are achieving distributed AI. From very high bandwidth requirement, we are moving to the reduced bandwidth. From high centralized computing power, we are moving to we can use now small devices which have small computing power and yet can provide inferences, and potentially high latency. In case of clouds, we are able to provide the real-time response because the device is with you, no internet connection is required, and it totally the response is instantaneous. Plus, at the same time, we are preserving the privacy. So these are the reasons why we are looking at AI on the edge, or we are taking AI to the edge. Our bandwidth requirement, our power consumption, cost, latency, and privacy, and so on. I'm not sure who unmuted. Can you please mute? Yep, thank you. So inferencing is going to be everywhere on your mobile, on your car, on your drones, on everything, on your mobile or whatever device that we are using. Every electronic device can be turned into a tiny AI, a tiny intelligent device, which can be used for, which can provide intelligence in your day-to-day activity. Now let's look at what are the technical areas. What is the technical area that is deriving this tiny ML or the HM? First of all, machine learning is always going to be there. That is because that is where the intelligence comes from. Second is the IoT devices that will be required, right? IoT devices and operating system. Of course, Linux is just for the namesake. There will be some operating system or some operating system which is good for both embedded systems and your machine learning, where both can be reside together. So cloud, edge, and tiny ML. So these are going to be the tech enablers. So IoT devices, machine learning, and the embedded systems. So they need to be together. They need to come hand in hand. Then only these kind of things. This is possible, even possible. We'll quickly show a workflow as well. So hope you are already aware of system on chip. If you're not, Raspberry Pi can be taken as a good example of what SoC is. It can have multiple processing units. For example, this is a block diagram of a SoC where there is a main processor. There can be a GPU. There can be a DSPs. There can be several accelerators. There can be some other sensors as well, right? So these are small, very handy devices, small devices which can have processing power, but very limited one. And these SoCs are being used for enabling the tiny or edge ML. So a very good example is Raspberry Pi, which maybe we are the most familiar with, any SoC that we can see. So what it is an integrated circuit. It has a CPU, a memory unit is very limited, IO input output and secondary storage limited, but there can or may not be have it may or may not have other units like GPUs or DSPs and so on. Right. So we are going to talk about SoCs now for the implementation per se. And I'm not going to detail of SoC, rather from implementation per se, how tiny ML is getting enabled. So we'll require some optimized hardwares. When I say optimized hardwares which, if I just like CPUs, we have to come to GPUs and TPUs for the cloud-based ML, where all the processing was done on the graphic processing unit or tensor processing unit when the problem was of scale. Similarly, we require optimized hardwares, optimized processors, which can go in and run those artificial intelligent models on their own. For example, these are few of them which are already in the market: NVIDIA Jetson, Google AI VisionNet, and Neural Compute Stick from Intel. So these are few SoCs, small chips, which are ready to run ML-based algorithms on their machine, ML-based inferences. Let's see what actually happens if we are looking. So let's talk about a manufacturing unit where the task is to create this small chips which are getting created. So these sensors can be in, and which can signal whether this is perfectly okay, or this is a problematic chip, or whether the dimensions are getting adhered to whatever it has been there for anything. So now there will be having a managed IoT connectivity service, which will connect between cloud and your sensors on your devices, or low power wide area network modulation. So this enables the connectivity, this managed IoT services, so that we can communicate between these two. And a neural network, which is now trained on GPUs or on the cloud, can this is what happens when we are talking about the cloud ML, but it moves on to the left side, that is on the devices side, and the updates are provided over the firmware. So now if there is a problem, say example in this one where this brown signal is there, only that information goes in and needs to be sent to cloud, not all the information whether this is okay or not, because wherever there is no problem, no need to send any information to the next level. Right. Only thing that is faulty or required a support or required a maintenance or required some information, some meaningful information to be sent, only that information needs to be sent to your cloud or for further responses. And only for those the devices will come in response. So right now we were talking about SoCs. Now synthetic sensors is very good innovation that has happened recently. And for example, there can be multiple sensors which can go into one single chip. For example, a sensor which can detect lightning, a sensor which a voice modulator or encoder or voice modulator, or say environmental sensor, or or pressure sensor or air quality sensor. So all those sensors can go in one single chip, and we call that as a synthetic sensor. Would like to play a small video, quick video that can tell you what kind of innovations are actually going or happening right now. So hope all these links are there in the PPT, so you don't have to worry about that. I'll be sharing those PPT. Hope you can hear the audio as well. Uh, So you got some idea of what we have been talking about and what kind of sensors will be required and what kind of intelligence is going to be provided. So one small chip, can do, or a few small sensors being merged together can act as the intelligence provider for your entire room or for different activities that will be needed. Okay. So this was some awesome project which is being done, and there was a good paper along with that. So we have links there. We'll be sharing the PPT after this. So what actually is required for this enablement? So we capture the data, we clean the data, so all these three stages are kind of ML stages, which still remains the same as it used to be. But once the model is trained, once the training is done, once this training is done, we pass this, we have to change our big model, which had say billions of billions of parameters into optimized code, and code is optimized for say microcontrollers or small devices, and then it can be shipped to a small to these to microcontrollers. So what actually will be required? Or what are the challenges? Most MCUs today do not have the memory and processing power. We need to have those optimizations done. MCUs run DNNs themselves, provided they are optimized by MCUs. That is microcontroller units. They need to be optimized for running DNN algorithms. This is going to be same analogous to how requirement of GPU came in once the CPU was CPUs were not enough for running big models. Same thing is going to happen, or same revolution is going to come at the microcontroller level, where now the new microcontrollers, they are going to be optimized in such a way that they will be able to run these deep neural models. Okay. So how we are going to enable this, or what are different engines or different options that are there already in the market? We have TensorFlow Lite, that is for AI at the edge. We have some EIQ or NXP implementations as well. This is from ARM, I guess, and TensorFlow Lite Micro for different MCUs. So if you can go in, look at more. I know this was just an introduction that these things are being done, and to actually move it to edge, these are the frameworks which will be required, which can be used to move it on the edge. So what is now going to happen? So Xcube AI is one such framework which is already there. So this workflow shows that. So we have this training and validation phase again that happens still on the cloud. That is still happening on the cloud, whatever is in the red box. But once that is done, the deployment on some MCU is going to happen, and Xcube AI package that makes that enables that. So this is open source package which can be used to deploy optimized DL models on your sensors, on your edge devices. So there are multiple frameworks are available already, and this research field has come up only in 2018 or 17 after that. So it is pretty new, and maybe looking for you all guys to go in and do some machine learning on the sensor side. We'll leave that just to show you what is the going to be the requirement of the MCUs. So activity tracker, different kind of activity trackers require different kind of different processing powers. For example, just to do activity or motion sensing, only a 10-second MOP is going to be good enough. So MOP is operations per second, that is million operations per second. G is going to be, say, billion operations per second, which will be required by audio processing or speech recognition or object detection kind of thing. For more advanced things, we may still require one or two POPs, which are going to be pretty heavy from the requirement per se, because that good amount of processing power in sensor will really cost more. But for all practical applications, for most of the practical applications, these two are going to be good enough, and for which your phone or smaller sensors are going to be good enough for any such applications. So for till when we were moving on to the cloud, it was like we are going all ballistic, use anything, use as much as you want, but it is going to be the reverse way. We cannot have very big models, because now our memory requirement is going to be, our processing power, our memory requirement are going to be very constrained. So when we are dealing with, so these Cortex processors are most popular ones, which are available almost in all mobiles or for small sensors. These are produced by ARM, and they are already saying that they have probably shipped 200 billion such intelligent sensors, and they are producing, say, more than 900 per second or so. This is the data by ARM organization. So these are having, say, 32 KB memory, 128 KB memory, 384, and so on. And if we have in GBs, we are really lucky to have that kind of thing. So from all the TB memory and GPUs processing powers, we are coming back to saving the world, where we'll be using using our resources in a much more smaller way, or much more restricted way, and that is where all the focus is going to be. So these are the new challenges, and this is some of the ways that we can deal with. For example, we already have parameter efficient neural networks. We mobile net and squeeze net. There are two different papers. These are the name of the papers, in fact, which propose different techniques of compressing the neural networks to a size such that it can be fitted into a sensor. So a neural network which was of MBs can now be reduced to, say, 100 KB or 150 KB and built on the sensor itself. Pruning and truncation, this is another way of making the neural network smaller. By neural network have billions of parameters, and actually once they all are the initial hidden states, they are mainly a feature detector. So if we can go back and see what we can prune, whatever is not used, we can scale down our neural network to a great extent, and that is what pruning and truncation do. Distillation is kind of making use of transfer learning. That is a big neural network which was trained on very generic problem statement can now be used as a teacher to guide in the smaller neural networks uh, uh, to quickly train them, and the size of neural network are going to be very small. And of course, we'll be requiring the optimized microprocessor designs. For example, this is Jetson Neo, and this is Google's device. This is just for your reference if you ever need. So the slide is there. It contains what are the devices that exist today, which are being used in TinyML, and what are different frameworks which are there, which can be used for this purpose. We have the link and the data for that. So now, why this is going to be a revolution? You can see 1% was on Cloud ML. Usage went up to 4% when we are talking about the edge, and 95% usage is still there that we are looking at, and which will come through with the help of TinyML. So the models are still going to be the same, but they will be much squeezed, small, and small in the sense that they can even be fitted on KB's memory and still provide the inferences and intelligence to us. These are a few references and few further readings for you. And thank you. So that was for me.
Yeah, thank you, sir. Thank you. That was a wonderful, productive lecture. Now, from the participant side, if you have any queries, you can ask me.
Hello, sir.
Yes.
Yeah, sir. This was a very good presentation. So I have one doubt that everything is now going online based on AI, IoT, and all. So you also said something about cloud things and all. So the question is how this data security is going on. Means whether it or knowingly or unknowingly we are giving every data through cloud. Means all our data is in cloud through our mobile. So whatever the data security, can you talk some on that?
Okay, so see, first of all, there are different compliances, different rules and regulations already in place. So if we are thinking that unless we are sharing those data on social media explicitly by us, anonymous data is not going to be that easy to be sent onto the cloud, because they are now restricted by so many compliances, laws of different regions. So that is already happening. So it's not like they are going to collect anonymous statistics unless we explicitly allow them. For example, we may not be caring by saying yes, by enabling, okay, give access to my photos, give access to everything on our mobile phone when we are enabling. If we are careful while we are doing that, it is not going to happen. Plus, the TinyML, the Edge ML has the edge here because we are not sending all the data that we are going to use to drive out inference to the cloud. Rather, the data is still going to be remain on your mobile phone or on your device, which or on a sensor which is inside your home, and no data or is going to be sent, or anonymous data which is only required for improving the model further. They are going to be sent onto the cloud. The privacy and security is the most important thing that this IoT or AI at edge actually addresses.
Yes, sir. Actually, I would like to narrow down my question. So when a cloud-based AI is implemented, so always they need some data. So
Right.
for the data only, based on the data only, they are going to develop the AI model and train the models like that. So let's say we take an example of Alexa. So to improve the response, so Alexa is going to store my day-to-day activities, right, sir?
No, it do not happen like that. Normally,
Okay.
it happens is the model is already built. So Alexa is providing the response on the basis of your neural networks, which are already built and shipped on your mobile phone. So the response that is getting provided, it is provided on the fly then and there. Okay.
Yeah,
Some
okay, but
go
I
to the
wanted to
cloud.
say that if I are browsing in YouTube, so next time I log into YouTube, it will show recommendation based on my previous search. So in a way, I can say that my previous search are being stored by Google. That's why it is showing me a specific search results. That is what the question
That is
was.
different. Yes.
Yeah. So in that case, all my previous search history YouTube has recorded, and it is with them, and it is only the law enforced by the government that is it is safe, nothing else.
Right, right. So that is a different thing. The data which our sensors are providing or our mobile phone is providing, that is for model training purpose, that is a different thing. What you're saying is your data is getting stored on your cookies and your data is being shared. Google is already tracking whatever you are doing on your laptop. It is because you have given that permission already, whether knowingly or unknowingly. We are enabling that permissions, and if we want that privacy, that much security and privacy, we need to be very careful what we are enabling or what we are allowing for Google or everything to track.
Yes, yes, right, sir. That we should be take care of. But the
Yes.
problem is that there are some application without enabling permission, it will not work. So that's a separate case.
Yeah,
Okay,
that's
thank
it.
you, sir. Thank you for answering my questions.
Do anyone have any other questions? Please ask.
Okay. So I hope that you got some idea on the edge AI side or machine learning on the sensor side, because you being from electronics background, this is the area that comes from your purview. The, the way machine learning took off, this is going to be more revolutionary, and with the age is going to be again back for you and you guys to do more innovation.
Fine, sir. Thank you very much. Thanks once again for the wonderful as well as productive speech, because all those things are definitely will be useful for the participants at some point. Thank you very much.
Thank you. Thanks for everyone.
And dear participants, just give me a minute. Uh, the resource person will be joining shortly. Please give 5 minutes time. Uh, Hello, sir. Winston, sir. Hello.
Yes. Yeah, I'm available online.
Sir. Yeah, yeah. I thought you were not there, sir. That's why I am searching for you.
Okay,
Good
okay.
evening, sir. A warm welcome to the short-term program on electronics instrumentation and control communications. Just, just give me a minute.
Shall I share my screen?
Yeah, yeah. First, let me introduce you, sir. Then we can share your screen.
Yes, yes, yes. Yeah, yeah, please.
Dear participants, Dr. Winston is currently working as assistant professor in computer science and engineering department, NIT Srinagar. He holds PhD in computer science and engineering from Anna University, Chennai, and his expertise areas include machine learning and its application in natural language processing, individual/group modeling of web users, web users search behavior, topic modeling, personalized web document ranking, image re-ranking, and computational intelligence techniques. His current research interests include applications of deep learning in NLP, text summarization, social network data, and review data analytics. So with this short introduction, I would ask Dr. Winston sir to take over the session.
Yeah. Thank you for your introduction. I hope I can share my screen now.
Yeah, please do sir.
Yes, thanks. I hope my presentation is visible to all of you.
Yes, it's visible properly, sir.
Yes, so we are already. Yes. All right, so let's get started. So the topic of my talk is going to be on exploring deep neural networks. So I hope some of the aspects that we're going to talk about have been already discussed in the previous sessions. As I have seen the glimpse of the previous talks, I could understand that all of the talks are actually relevant to the neural network notions. Okay? So in that respect, let me focus more on deep neural network, and possibly I'm planning to spend more time on demo than seeing theoretical stuffs. So I hope that enough materials have been already discussed by the previous speakers. So in this talk, I'm going to focus more on some sort of healthcare prediction application. So let's try to demonstrate it with the help of deep neural network. So this is how I'm going to spend time on various points to be discussed. Is there any problem with my line? I hope I'm audible to all of you.
Yes, sir, you are audible. But sometimes the screen goes blank and then comes back.
Okay. Okay, let me just stop sharing and let me do it again. Sharing it again, I hope it is visible.
Yes, sir.
Yes. So first, let's see the various classification of artificial intelligence, which is going to be more generic. And then since the demo is going to be based on deep neural network, we use any neural network, especially for learning. Okay? Let us understand what learning is actually all about. Okay? And then we shall see a few applications of AI in the healthcare domain. And then let me also touch upon a few preliminary things corresponding to deep neural network. So, and then straight away we shall jump into the demo on a data set of healthcare prediction, and let's model it by using deep neural network. So AI is generally classified into 4 different categories. We shall see them one by one. So AI could be classified. The one class of applications are termed as automated intelligent systems, where repeated tasks could be automated. Okay. For example, repeated task in the sense you could completely automate them without any sort of human involvement. Okay. For example, if you have ever visited shopping malls, as you get into the shopping mall, and the head count will be taken, and the machine will be placed right in the front of the entry gate, and as you pass through the gate, and your head count will be taken.
So this task is going to be repeatedly done for every person who enters into the shopping mall. Okay, so this is one of the repetitive tasks which could be automated with the help of this type of automated intelligent systems. Okay, so where human involvement is not at all required. Okay, so it could be completely automated, and it is possible only for modeling repetitive tasks. Okay, whereas coming to the other class of AI, category, which is known as assisted intelligence. Okay, which essentially automates or assist the system which have been already managed by the human being. For example, you can think of now automating any task which has been already done by the human being in the past. Okay, so we now observe a lot of such assisted intelligence systems in every sector. Okay, especially you can think of automating the conduction of election task. Okay. So earlier, every task related to election, conduction of election was actually carried out by human being manually, and now some of them could be automated. Okay. So in the same way, you could see now some of the things which have been done by the human being manually has been getting automated. So in this case, the assisted intelligence system could be used in order to get some recommendations, and then further final decision is going to be essentially taken by the human being. So here the human involvement is required in order to make the decision. Make the decision. And the third class of AI applications are known as augmented intelligence systems, which is actually powered by machine learning and deep learning stuffs. Okay, so where we are essentially trying to learn from data, especially from the past, the data which has been observed in the past. So again, in this case, so we are going to come up with some sort of automated intelligence system, so which will make decision, and the made decision will be evaluated by the human being. Okay, so the augmented intelligence system, the difference between assisted intelligence and augmented intelligence is that the assistant intelligence is going to simply automate the tasks which have been carried out by the human being in the past manually, whereas the augmented intelligence system is actually powered by machine learning, deep learning stuff, so as to get more insights from the data. Okay, and finally, it gives us the predictions or some sort of outputs. The same will be evaluated by the human being. And finally, coming to the fourth category of AI applications, AI category known as autonomous intelligence. And the well-known example for autonomous intelligence is the driverless cars. Okay, where human involvement is not required, whereas the time to time the periodical decisions will be automatically taken by the system itself. Okay, again, this autonomous intelligence is also equally powered by ML and DL stuffs. Okay, but the thing is here the evaluation of the prediction of the model is also going to be done automatically by the machine, which means the decision is going to be taken by itself. Okay, among these four classes of AI applications, and in this talk, I'm going to focus more on the augmented intelligence. So where machine learning, deep learning plays a vital role, and deep learning is a family of ML algorithms. And under the umbrella of deep learning, so we have various families of algorithms. So we shall just see some random configuration or one specific configuration of deep learning, which could be fairly understood. So first, let me define what learning is all about. Okay? So learning essentially comes from the data. Okay, so we must have data in place, in order to initiate the learning, and moreover, machines actually learn from what we teach through the data. Okay, because machines generally do not have the mental model, the way how human being essentially do the the reasoning. So the same way machine cannot do the reasoning. So we supposed to teach the machine in such a way that it can learn something from the data. Okay. And coming to learning, I can define the task of learning as identifying a function which approximates the relationship between x and y. Okay, so in the context of machine learning and deep learning, so we would very frequently use these terminologies, X and Y. Let's say X is going to be my input. Let's say my input X contains a lot of features. Let me name them as X1, X2, and so on and so forth up to, let's say, X100. So assume that every entry in my data contains 100 values. So every row in my data contains 100 features, and features are named by X1, X2, and so on and so forth up to X100. Okay, so you can think of this as an 100-dimensional data, where every data point is going to be denoted by 100 values. Okay, generally, in most of the applications that we deal with, in all those applications, data would be in real form. So it would be a real number. So all these values are going to be a real number. And then we would have corresponding Y label. For example, let me orient this example towards the demo part, so which we will be shortly getting in. Okay. So I'm going to deal with data about heart disease prediction. So the data could be used for modeling, or we can come up with a deep learning model so as to make prediction, okay, on any new patient, whether the patient would be diagnosed with heart disease or not. Okay, so it's a very simple classification problem where we deal with a binary class classification problem. So it's a binary class classification problem where the model would predict whether the person would be diagnosed with heart disease or not. So in case if the person is diagnosed with heart disease, so let's say we are going to assign the label 1. In case if the person is not going to be diagnosed with heart disease, then we are going to assign label 0. Okay. So in order to train a model, so we require the data which has been recorded in the past. Okay. So assume that I have 1,000 such rows, which means I have 1,000 such patients data. Let's say this is the first patient data. I have 100 features for this patient, and then this person was actually diagnosed with heart disease. Similarly, I have my next row of data. Again, I have 100 real values, each corresponding to different features that are considered here. And then assume that the label assigned to that patient is actually 0, which means the person has not been diagnosed with heart disease. Okay, so in order to learn, or in order to come up with a machine learning or deep learning model, so we must have data which includes both X part as well as the Y part. Okay, so X part is the features. So X part denote the features, and then Y part denotes the target label, or the actual label, or true label, and so on. Right. So now once we are provided X part and Y part, then there would be some true relationship which exists between X and Y. Okay, so let us call the true relationship as F. Okay, so there is some true relationship. There is a function which maps this Y, this X, let's say, to a Y value. But in most of the practical scenario, this true function F is unknown. Okay, so this is completely a complex and composite function, so which is generally unknown. Okay, so since this function is unknown, because if this function is known, then this problem is straightforward. Okay, we don't require any sort of learning to perform in order to map the given X against Y. Okay, so if this function is known, we can straight away map this X to Y. Given X, we will be straight away able to say whether the person will be diagnosed with heart disease or not. Okay, so since this function is practically it is actually unknown, so we want to come up with some function, let's say F hat, which approximates the relationship between X and Y. Okay, so coming up with this function which approximates the relationship between X and Y is what requires the task called learning. Okay, so we learn this function F hat because this function may involve some number of parameters. So this function will deal with some number of parameters, and we come up with this function by learning those parameters through which we'll be able to map X with the corresponding Y. Okay, so coming up with this this function which approximates the relationship between X and Y is what known as learning. Okay, so basically learnings could be of different types, and generally we have two major types of learning. One is supervised learning, another one is unsupervised learning. So in case of a supervised learning, we'll be provided with both X as well as Y. It will be provided with X and then its corresponding target label, and then we'll try to come up with a function which approximates the relationship between X and Y. And in case of an unsupervised learning, and we will be provided only X, so we will not be provided Y column. So Y column will not be provided in case of an unsupervised learning task. Okay, I'm going to focus on the supervised learning task because most of the problems that we see, okay, in any domain, especially in finance sector or in healthcare sector or in any sector which deals with data, even I can say every department in an organization. Okay, so every department in an organization actually comes up with a lot of problems which can be solved with the help of machine learning or deep learning. In case if we consider HR department of an organization, of any organization, so HR will have a lot of problems, and for which they will have data with them, and they may be trying to solve those problems, and most of the problems that they have are of type supervised learning, which means they will have both X value as well as the Y value for their data, so that we'll be able to do some supervised learning over this, so as to come up with this function. Okay, so when I say this function f hat, and you can think of this f hat as the various machine learning deep learning algorithms we have. Okay, so in case if you are comfortable with let's say some algorithms under the umbrella of machine learning called SVM, so you could approximate the relationship between X and Y with the help of SVM. So then SVM is, let's say, your f1 hat. So this is one of the functions through which you model the relationship between X and Y. So similarly, you could also use, let's say, a naive Bayes algorithm or a naive Bayes classifier through which you can even try to model the relationship between X and Y. And then you could come up with, let's say, some ensemble family of classifiers. That would be your next model. Okay, and then you could also go with some sort of simple neural network family of algorithms. You can call them F3 and so on, F4 and so on. Okay, so each of these machine learning algorithms are what the models which approximates the relationship between X and Y. Okay, so as part of the demo, we are going to talk about one such model. Okay, so essentially, since we don't have any clue on this true function f, so we have to somehow approximate it. Okay, the only way with which you can approximate the relationship is by getting some logic or clue from this X and Y. And moreover, we have various choices for this function, which is going to act as an approximation. Right? So these are some of the choices we have. So you could go with some of the machine learning family of algorithms, or you could go with some neural network family of algorithms. Okay, so under neural network family of algorithms, we have a lot of algorithms. Okay, so one such model is what? Deep neural network. Okay, so when I say deep neural network, I don't really mean CNN or RNN. These are some of the buzzwords which comes in hand in hand whenever the notion of deep learning or deep neural network comes into picture. Okay, so the neural network which I am going to talk about is known as deep neural network, and later let me define why do I call it deep neural network. Why not just neural network? Okay, so I'm not going to talk about CNN or RNN, but I'm going to just talk about some flavor or some family of neural network algorithm, which I call it deep neural network. Okay, so we shall also see the reason why do I call it deep neural network. Okay, and these are some of the problems which cares about learning task. Okay, so in addressing all these problems, a learning actually happens. Okay. So this the application which I have explained here, with the help of the hard disease data set is a kind of classification task. So here it's a very simple classification which deals with binary class. Okay, so the predicted class is going to be either 1 or 0. So you can also have think of multi-class classification problem where you deal with multiple classes. Let's say you wanted to come up with a model. Let's say you want to come up with a model which takes an input as an image, and you want to map the input into one of the 5 categories. Let's say you have 5 categories of images. Let's say car, and let's say bus. Let's say flower. Okay, and let's say animal, and then let's say some sort of monuments. Okay, monuments. So let's say given an image, I may want to design a classifier or model a classifier, so which takes this image as an input and it maps it to any one of these classes. Yeah, so this could be termed as multi-class classification problem. And then next we have something known as anomaly detection, where you may be trying to detect the anomaly, and the commonality in all these applications except this clustering. So except this clustering, remaining all are supervised classification. Okay, so let me give some precise details about each and every one of these applications. And coming to anomaly detection, again, assume that you are given an image, let's say containing eye retina image. So let's say that you are given a retina image and you want to come up with a model. Okay, so which can find out in which part of this retina image there is an anomaly. Okay, so in order to train such a model, you must train or learn a model with at least thousands of images. So let's say that you have 1,000 such retina images, and some of them has anomaly in it and some of them do not have anomalies in it. Okay, so let's say if there is an anomaly, let's say this is my image which I'm going to use it for training. So it is a retina image, and assume that I have a bounding box around the anomaly where it exists in the image. Let's say that I train a learning model or train this anomaly detection model with 1,000 such images. Okay, so for which the X part is going to denote, the X is going to denote the image part. Okay, so when you represent image for actually the learning task, we would consider pixels from the image. Okay, in case if the image is let's say 30 cross 30 image, then we essentially deal with 900 pixels. Okay, so you will have x's starting from x1 and it will go up to x900. So we deal with 900 features. Okay, so we will also ensure that all the images are of same size. Right? Now, what is going to be y part? And y part is going to contain the dimension of this bounding box. Okay, so this bounding box essentially covers the location where the anomalies exist. Okay, so let's say I define this boundary by let's say 4 values. So let me write it as let's say x1 and y1. Okay, x1 and y1 denotes this point, and then I also specify the height and width of this bounding box. So with these 4 values, x1 and y1, and then w and h, so I will be able to represent this bounding box on this image. Okay, so with these 4 values. So now for every x, you must also have this y. And if you have at least 1,000 such images, so you will essentially be able to learn an anomaly detection system, so which can work on some unseen images. Okay, so in case you have a retina image, you want to check if there is an anomaly exist or not. So you can test this model with the help of an unseen image. Okay, so based on the learning it has done so far on the existing data, so it would make the prediction. So whether there is an anomaly or not. In case if there is an anomaly, it will also specify the bounding box on the location where the anomalies actually exist. Right. So and then object identification. So object identification is also very similar to anomaly detection. So in case of an object detection, so I wanted to detect various objects in it. Okay, let's say I give an animal image. Let me take some random image. Let's say there are a few objects in it, and you will have to. The image is going to be your x, and then the y is going to be the dimension of the bounding box which covers the various objects present in the image. Okay, so you must at least train such model with, again, at least some thousands of images. Okay, so the more the data you have, you'll be able to better learn. Okay, so that's the reason why I say everything in terms of thousands. Okay, so it doesn't mean that only if you have thousands of data points or thousands of images you'll be able to learn something. No, it is even possible at smaller scale as well. So even with 100 points, you will still be able to make some meaningful. You will still be able to do some meaningful learning, and you will still be able to get some outputs. Okay, so the input, the data that we are going to deal with, is actually containing a few hundreds of points. Okay. And then coming to prediction and forecasting. So in case of a classification task, so we are actually interested in some discrete value output. Okay. So if it is a binary class, then we are interested in value either 0 or 1. In case if it is a 5-class classification task, we are interested in, let's say, I just call car as 0, bus as 1, and then flower as 2, and then animal as 3, and then monument as 4. Okay. So again, we are interested in some discrete value output in case of a classification. But in case of a prediction, so we are actually interested in some real value output or continuous value output. Okay. And coming to forecasting, again, example for prediction could be, you want to predict, let's say, it's also similar to anomaly detection is a kind of prediction task. So you are actually predicting the location where the anomaly exists. So the output of this task is actually 4 real values. Right? So this could be any 4 values. Okay. So provided that it must be restricted to the boundary of the image. Right. And coming to forecasting, so forecasting deals with time series data. So you want to predict, let's say, you want to forecast the share price, let's say next month. Okay, there is a company which is trading in stock market, and you want to predict the price of it tomorrow, or you want to predict the time of it, let's say by 2 o'clock, in the afternoon tomorrow. Okay, or you may want to forecast the share price probably the next month. So next month, what would be its growth? So whether there will be an increasing trend or there will be a declining trend, and so on. Okay, so for which we will be using some time-stamped data. So the data which is recorded at every time point. And then coming to clustering, so which deals with just X part, and the Y part is something which is unknown. Okay, so you just want to restrict your learning only towards this X part alone. Okay, so the very familiar task under such learning task is clustering. So you assume that you are given hundreds of images. So you want to cluster them into, let's say, some multiple groups. Let's say you want to cluster them into K clusters. Okay, so you have one group of images where all the motor vehicles are present. Okay, so and then you have another category of images where flower images are present. Okay, so you try to come up with some pattern, so only from X part itself. So you are actually trying to relate X with itself. Yeah, accordingly you are going to represent your output. Okay, and then the other category of applications are known as generation. So where assume that you want to learn a model with let's say some 1,000 paintings, and you want to generate your own painting automatically through the learned model. Okay, similarly, you can also automatically generate text. You can automatically generate text. Okay, so the well-known example for generation is that the chatbots. Okay, so chatbots actually generates a text. Okay, so it gives us the feel that there is a human being sitting at the other side who is giving response to our queries. Okay, so it could be either image generation or video generation or voice generation or text generation and so on. Okay, and then coming to language processing, so anything which deals with linguistics things, then we call them as language processing applications. So again, a lot of learnings are lot of learning happens there. Okay, so even in your simple chat application, you might have seen as you type, and it helps you in autocomplete. Okay, so it gives you some recommendation. So what would you type next? So even the same thing happens even in Google search engine as well. So as you start typing your input query, so it would also give you some 10 plus recommendations. Okay, so it is it actually learns something from the previously entered queries, or it might have been learned from some previously observed piece of texts. Okay, so accordingly they come up with some sort of recommendations. Okay, all such applications comes under language processing task. So even there, a lot of learning happens. So these are various application areas. So I believe that these application areas would have been already covered in at least one of the previous talks, as I have observed from the previous speakers. I think some of them have spoken about some of these stuffs. So let me skip this for now, so that I can devote some a good amount of time on demo. Okay, so with this, let me straight away jump into demo. And for the demo part, I'm going to make use of the hard disease dataset, which is provided by UCI repository. Okay, so there are various data sources from which you can actually collect data for your machine learning or deep learning tasks. So one popular data source where you can find hundreds of interesting data sets is the UCI repository. Okay, and then most of the data found in this UCI repository is also found in the portal called Kaggle. So Kaggle is a portal where you find a lot of MLDL challenges, and they also post the challenge along with the data sets. Okay, all of them are freely accessible. If you have login with Kaggle, even some of the data sets are even accessible without even having any login to this Kaggle portal. Okay, so these some ready-made or already prepared data sets would be available from these sources. In case if you want to populate your own data set. So let's say you deal with some machine learning, you want to learn something from data, but the data is not available. So in case if the data is not available, so what you could do is, so you could generate your data. Okay, so probably you would have, let's say, X part. Let's say that you lack Y part. You don't have Y part for your X data. For your data X, you don't have the Y part. So what you could do, you could ask some third-party people to do that. So on your behalf. Let's say you have some 1 million images with you, and you want to put a bounding box over all the images where some piece of English text is present. So let's say you have, let me just give you one such image. Let's say it's an image, and somewhere in this image there is some English piece of text. So you want to have a bounding box over all those images wherever text is present. Okay, and then what text it is. So you want actually two details. So one is the bounding box where the piece of text is present in this image, and then what text is present. Assume that I restrict myself to some English text. Okay, so assume that you have 1,000,000 or 1,000 such images, and you don't have time to do it manually on your own. So what you could do is, so you could just simply ask some third party to do the same thing on your behalf. Okay, so in that respect, we have something known as mechanical Turks. So mechanical Turks, even Amazon provides its own mechanical Turk through which you can post your task, and you could also price the task. So if somebody does tagging for one image, so how much amount will you be able to provide them? Okay, because this whenever if you do some task through third party, then you will have to spend some money as well. Okay, so in case if data is not available, so you could do it with the help of some mechanical Turks provided by Amazon, and there are other vendors as well. Okay, you can post your task, and you can also set the deadline. If you complete the task within the deadline, probably you promise them to pay some money. Right. Anyhow, for now, assume that we have data readily available with us. Okay, so the data which I'm going to deal with is about heart disease, and every data point is going to have 13 features. Okay. So I've given descriptions on each of these features, but features are not more important, because anyhow we are going to interpret each and every feature in terms of some real value representation. Okay, so let us not get into each of these features, but at least by reading the name of the attribute, you could be able to guess the meaning of some of these attributes, like age. Okay, so it denotes age, and it will have some range of values, and then the sex, gender is going to be denoted by 2 possible values, and then the CP, chest pain type, which has been observed in the past. Now all these data are actually denoting some past data. Okay, so these data are actually observed from the patients who have who have visited the doctor who is specialist in heart, who is specialist in heart, right? And then every data point also comes along with the target value. Okay, so whether the patient, because all these data are actually observed in the past, so it would have been either diagnosed with heart disease or it would not be diagnosed with heart disease. So you also have the appropriate label for them. So we now have both the X part as well as the Y part. Now, since we have both X and Y part, and since we do not know the real true association between X and Y, so we want to approximate it with the help of some function f hat, which I'm going to learn through deep neural network. Right. So the number of data points which I have as part of this data is actually 303, which is just few hundreds of data points. So still we'll be able to learn something. Okay, so let us also see whether there is some learning happens there or not. Okay, so just by observing the output of the classifier, because we are actually doing some binary classification task here, where the number of classes is restricted to 2 only. Okay, like yes or no, or 0 or 1. So whether the heart disease is diagnosed or not, right? And so that's the data that we use, right? And we are now comfortable with these two parts. We know the data which contains both X part and then Y part, and every data point contains 13 features along with its corresponding Y label. And then we have 303 such data points, right? And coming to a task, we define it, we want to implement it as a binary classification task. So we want to implement binary classification task, which means we want to learn a classifier, so which can take some unseen patient data, and it can give us a prediction. So whether the person will be diagnosed with heart disease or not, right? So what is going to be the model, and we are going to come up with some deep neural network model. Okay, so this model is what this function f, so which we are going to approximate. Okay, so there we have a lot of choices for this model, and and let us just stick with some deep neural network family of algorithms. Okay, and then assume that you initially start with, let's say, some random model, because whenever we say we talk about a neural network, I hope that some preliminaries of neural networks have been discussed in the previous talks. Okay, otherwise let me also touch upon certain preliminaries of neural network. Okay, so in neural network we have something known as neurons, right? The way you arrange neurons as part of your neural network configuration, so you would come up with different flavors of neural networks. Okay, okay, let me just graphically show you one of the neural network configurations which we are going to demonstrate. Right, so here are all my inputs. Okay, I just deal with 13 input features, so I give this 13 inputs to all the neurons in my first hidden layer. So let's say this is my hidden layer. Assume that this is my first hidden layer, wherein I have 16 neurons. Okay, so and this is my input layer, and size of my input, or the dimension of input, is actually 13. So I deal with 13 dimensional input, right? And then I have one more hidden layer. Let me call this as a hidden layer 2. This is first hidden layer, this is second hidden layer, wherein I have 8 neurons. Okay, and then I have 1 neuron in the output layer. So since I am dealing with binary classification task, so with just one value, I'll be able to interpret it to either 0 class or 1 class. Okay, and assume that every neuron will output some real value. Okay, every neuron is going to output one real value as output. Right. So similarly, since this is also a neuron at the output layer, so this will also output some real value. Okay, and I will make sure that the real value that this neuron is going to output is going to be between 0 to 1. So that in case if this outputs, let's say 0.4, and since I am talking about binary classification task, I can have a threshold, let's say 0.5. If the output value is less than 0.5, I can call it, let's say, 0 class. Okay, so in case if the value is let's say greater than 0.5, I can let's say if it is if it is greater than 0.5, I can call it a class 1. In case if it is less than 0.5, I can call it a class 0. Okay, so that's the reason why I restrict my restrict the number of neurons at the output layer to be 1, because one neuron is enough through which I can discriminate whether the data point should be classified as either 0 or 1, right? And here I have liberty to decide the number of neurons at various hidden layers, and moreover we can also decide to have even more number of hidden layers. So we have flexibility to add more number of hidden layers, and then we have liberty to adjust the number of neurons in every hidden layer. Okay, so in case instead of 16 neurons, let's say if I put one more neuron extra at this first hidden layer, so then the function is going to be completely different now. Okay, so as you make changes to this neural network configuration, so you actually try out with different function, through which you try to approximate the relationship between x and y. Okay, so now assume that you start with some initial configuration, and moreover every neuron will also deal with lots of weight values, so which are actually denoted by W1, W2 and W3. So W1 is a set of weights which are used in first hidden layer, and W2 is the weight, it's a weight matrix which are used in the second hidden layer, and then W3 is a set of weights which are used in output layer, right? And one more thing, if you look at this neural network diagram, so it is not complete. Just to have some visibility on this diagram, I did not connect this x2, x3, x4 with all the neurons in the first hidden layer. So actually you should connect all the inputs with all the neurons in the first hidden layer. Similarly, all the neurons in the first hidden layer should be connected with all the neurons in the second hidden layer. And then all the neurons in the second hidden layer will be connected with all the neurons in the output layer. Right? So I want this image to be clearly visible. So that's the reason why I did not add more connections here. Okay, I just done only few of them, but you will have to actually connect each and every input with all the neurons in the first hidden layer. Right? So every arrowhead that you find here, so all of them are actually associated with some weight value. Okay, so these weights are the parameters of the neural network configuration which has to be learned. Assume that you initially start with some random initialized weight values. Let's say when you run this neural network for the first time, so you initialize these weight values to be, let's say, some random values. Okay, you can also initialize all of them with, let's say, 1. Okay, but that's not actually a good practice to start with, because even for initializing weights we have various strategies available. So there are various mechanisms or methods by which you can actually initialize the weights for the neural network. Right. So for simplicity, let's assume that weights are going to be initialized at random. Okay. So even as you adjust weights, you actually make changes in your function. So function may be same, but the function is going to behave differently. So as you adjust the parameters associated with the function which you are trying to fit. Right. So assume that you initialize all these weight matrices with some random values. So now with the random values of these weight values, assume that you make the prediction. Okay. So how do we come up with this real value from this all these x values? And I have already assumed that the weights are going to be initialized at random. Okay. So assume that it is going to be initialized with some random set of real values. Okay. It can contain 0 values, it can contain some positive values, it can contain some negative values as well. And moreover, there is no range of values restricted. So you can have any real value as your weights. Right? I just go with some random values, and then over the time, now I'm going to adjust these parameter values. So that's what actually termed as learning in the context of neural network. Right? So I assume that every arrowhead that you see here is going to be associated with some input, and moreover, even our input itself is also a numeric input. So all these values present in our input are numeric. So the output or the value to be passed to this neuron, or at every neuron actually two things will be computed, so which are actually quoted in this diagram here, right? So at every neuron two things are actually computed. So one is called pre-activation, which is this part, and then there is an activation is computed. So pre-activation A is going to be computed as the weighted sum of all the inputs. Okay, so here at this neuron, the pre-activation is going to be computed as the weighted sum of all the inputs. Okay, let's say we have some value for x1, x2, x3, and so on and so forth up to x13, and then we have initialized this weight matrix. Okay, see, this W1 is actually a matrix. So because I have 13 input points, and then I have 16 neurons in my first hidden layer. So the number of weights that I need to learn at this layer, which means at this first hidden layer, is actually 13 cross 16. And then every neuron also takes some bias. Okay, so let me not get into the mathematical need of this bias. Okay, but anyhow, let me also give you some insight about this bias. And as of now, just remember, every neuron in the neural network is going to be accompanied by a bias. Okay, so this bias B1 is actually a vector containing, let's say, 16 values. Okay, since I have used 16 neurons in my first hidden layer, B1 is going to be a vector containing 16 real values. Okay, I denote it by R16. Okay, so it's a vector containing 16 real values. Okay, for simplicity, what you could do, what I have done in this diagram, I just assumed same bias value for all the neurons in the first hidden layer, and similarly the same bias value for all the neurons in the second hidden layer, and same bias for all the neurons in the output layer. So in this case, I just have only one output neuron in the output layer. Right now, I'm going to compute the weighted sum of all the inputs at this neuron. So it's going to be computed as the weight value corresponding to all the links which comes to this neuron. Okay, so this x1, 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 x2, x3, and so on and so forth up to x13 are actually connected with this neuron, and then every connection is also associated with some weight, and then you compute it like this. Okay, I can compute it like this, wx. So it's going to be computed as a dot product. Again, let me not get into the details of that. No, it's going to be simply weighted sum. It's going to be computed like this. Let's say x1 w1 plus x2 w2, and so on and so forth up to x13 w13. And moreover, the index is going to be differently used, but as of now, just understand that this is how the weighted sum of all the inputs, which is nothing but the pre-activation, is computed. And once pre-activation is computed, we can compute an activation. So here in this neural network configuration, there are various choices for activation functions as well, and assume that I have used sigmoid activation. So the sigmoid activation is going to be computed as 1 over 1 plus e raised to minus a. So this a is nothing but the pre-activation which I have computed here. So this h is going to be computed as a sigmoid function, which is nothing but 1 over 1 plus e raised to minus e. Okay, so the same thing is going to be computed at all the neurons in the first hidden layer. And then once you apply the sigmoid function on this a, so you are going to get a real number. So you are going to get a real number. This is going to be a real number. So this real number in turn is going to be supplied to the subsequent layers in your neural network. So similarly, in the next hidden layer, the pre-activation at this node is going to be computed as weighted sum of all the h1s. So here we have h11, and here we have h12, and here we have h13, h14, and so on and so forth. Okay. So in general, I just denote it by h1. So h1 is a vector containing 16 values. Right. So here the pre-activation at every neuron in the second hidden layer is going to be computed as the weighted sum of all the weighted sum of all the values which are outputted from the previous hidden layer. Okay. So the same thing is actually done, and we call this process as forward propagation. Okay, so as we propagate, as we move forward from input layer to output layer, so we call this process as forward propagation. Okay, so once we complete the forward propagation, so we will get some output at the output neuron. So once we get some output in the output neuron, you can try to interpret it. So once you, let's say you get the output from this neural network with some default parameter initialization, assume that you get some output, which I call it, let's say the output is 0.4. I call this as predicted output, right? Since I have data containing both X and Y part, and for the given data point, I also have the corresponding target label. So since I have the corresponding target label, for every data point which I use in order to train my neural network model, for each of those data points, I also know the corresponding Y label. Now, this neural network is used in order to make the prediction, and that's why I call it Y hat. The original target is actually Y, and the value which is predicted by the neural network is actually Y hat. Now, once you have Y and Y hat, you can compare both of them. So try to compare X and try to compare Y and Y hat. So try to find the difference between Y and Y hat. So in order to find out the difference between Y and Y hat, you can use the loss function. So the very simple loss function is known as, let me say it is squared error loss. So squared error loss is going to be computed this way. It's going to be simply computed as Y minus Y hat whole square. And in case if you deal with multiple data points, you just consider all of them. Okay, so where I goes from 0 to n, and then you do it on all the data points. So in case in your data set you have 303 data points, and among these 303 data points, let's say that you use only 80% of this 303 data points for learning your neural network model. So in case if you do that, then this probably 80% of 303 would be close to 240 data points, right? Okay, so now in this case, n is going to be 240. Okay, so for all those 240 data points which you are using for training your neural network model, for all of those data points, you measure the predicted output, and you also have the true output with you. And once you have both of them, now you can try to find out the difference. Okay, how do you find the difference? We compute the difference in terms of squared error loss. Okay, there are various choices for loss function, and the very simple loss function that can be used in case of binary classification is that the squared error loss. Okay, so let me do it for a few data points. So assume that let me just take restrict n to, let's say, 5. Okay. Let's say the first data point is actually classified by with 1. Second is classified the true labels. Okay. Let me better use different color. So let's say the true labels are 1 0 1 1 0, and this is my y. And my y hat is going to be, let's say, 1 1 0 1 1. Okay, so now you can find the difference between these two. So you are going to find the difference as y minus y1 y minus y hat whole square. So the reason why we apply square here is to avoid the negative value. Okay, because loss cannot be measured as a negative value. Loss should always be measured as a positive real value. Okay, so that's the reason why we add this square here. Okay, so 1 minus 1 is going to give you 0. So 0 square is also going to give you 0. Plus, here the true value is 0, but you predicted wrongly as 1. So there must be a loss added to this. So the loss is going to be added is 0 minus 1 whole square, which is nothing but 1. So this way, you simply count the number of data points which are wrongly classified by your model. Okay, accordingly, you compute the loss. Once you compute the loss, then you will have to back propagate the loss, by using back propagation algorithm, so as to update the weights for the subsequent iteration. Okay, in the neural network language, we call them as epochs. Okay, so for the next epoch, you will have to propagate the loss of the previous epoch and then try to update the weight for the subsequent epochs. Okay, so by propagating loss, backward, you are actually updating the weight. So again, probably let us jump into demo now. Then if there are more technical things to be discussed, probably I can discuss them along with a demo. Okay. So with this, I stop here and let me get into the demo. I don't know whether you will also be comfortable to execute a demo at your side. In case if you can also perform demo at your side, I can share the Python notebook which I have prepared. Okay, let me switch presentation to demo. In order to execute my demo, I have configured Anaconda Navigator at my system, which provides a lot of editors, and the editor which I am going to use is the Jupyter Notebook. Okay, so this Jupyter Notebook also comes as an independent editor. But I am using Anaconda Navigator here. So you can launch this Jupyter Notebook. Once you launch the Jupyter Notebook, it will open it in a browser screen where you will find all the folders in your Jupyter Notebook, right? So all the folders which are there, and then one which I have created for this demo is actually this. Okay. You want me to share these files with you now, with participants now, if you can do the demo, or I can do the demo now. Probably I can share the documents with you. Probably you can work with the dataset offline.
You can share it, sir, but however the session is being recorded, we will share to the participants.
Okay, fine. But I don't have access to chat window. I will let them share the documents. Probably I can at the end of
We
the.
will all together communicate to the participants later, sir.
Yes, yes. Then let's proceed with demo. Okay. So this is the notebook which I have prepared for the demo, and so this demo is going to be based on Python. Python is more comfortable to design neural network models in order to learn something from the data. Okay. So if you are comfortable with Python, probably you will be able to understand what these import statements are. The many things in Python actually comes from various libraries. So you need not actually write program or code for everything. If something which is already implemented by someone, why don't we make use of them? Okay. So in that notion, all these things are imported here as part of this notebook, and we use them in our demo, right? Right. So let me skip all these the import statements as of now, right? And now the first thing which I'm going to do is I'm going to load my data set. So here is my data set, which looks like this. So it's a numerical data which contains 303 data points, okay? And it contains 13 features starting from age, and it goes up to this null, and then the target is the target label. Okay, so for first few entries, you see all of them are actually labeled as 1, and then as you scroll down, and you would see some data points which are classified or which are classified as labeled as 0. Okay, so this is our data set in which we are going to use. Right. So now the data set is in the form of CSV file. So since the data set is in the form of CSV file, okay, so since my data set is in the form of CSV file, so I just use this read CSV function so as to read my data set from CSV format, and I'm putting it into something known as pandas data frame. Okay, this hard underscore data set. So this is pandas data frame. So I'm using this pandas data frame so as to represent my input. Okay, so once you import the data from the CSV format, and it gets now resided in this pandas data frame, and now you can do certain operations on this. And if I want to check the size of my data set, you can just simply invoke this shape command so as to see what is the length and height of your data set, the number of rows and columns in your data set. So here the number of rows here is 303 and the number of columns is 14. So including the target label. So excluding target label, we have only 13 features. Okay. And now if you want to see some first 5 rows from your data set in the form of pandas data frame, so you can use this head command, and if you do it, and you'll be able to see the first 5 rows from your data set, so which you already have here. So these 5 rows are actually getting printed as we invoke head. Okay. So just to see if the data gets loaded into pandas data frame correctly. Okay. So now you could see that data gets loaded correctly as per the format which you have. Now if you want to see some properties from your data set, you can invoke this info call. So this info function is going to tell you, are there any null values present in your data set? So this data set is completely cleaned version of your data set, where we don't find any null values as part of this data set. Okay, so it doesn't have any null values, and all the 303 rows are actually having no null values. And moreover, all the data, all the features are actually numeric features. So that's what this intent float denotes. Okay, so we don't have any categorical, we don't have any non-numeric attributes. All the input attributes are numeric. Now again, this is another way of checking whether we have any null values as part of these attributes or not. Okay. So if you see these attributes, none of these attributes actually having null values. So that is what is obtained by this. Then next, these are some of the pre-processing or some sort of, we call this formally as data visualization. So we just see some sort of features from the data before actually applying the learning model. Okay, so we call this as exploratory data analytics, data analysis, in order to visualize data from different angle, so as to see if it's the right data we have in order to learn something from it. Okay, so here, so we just see the distribution of both the labels. So how many data points we have which are labeled as 0, and how many data points which are labeled as 1. So that's what all that we see here in this plot. Okay, so we just plot it as a bar plot here, and we take we find the number of entries which are labeled as 0 and number of entries which are labeled as 1. And now we observe that there is a difference of 10 here, not 10. I think there is a difference of 20 here, which is not a much difference. Okay. One more thing that you need to observe: the number of entries that you have on 2 different labels should be almost equal to each other. So in case if you have more data points which are labeled as 1, then that would overperform compared to the other label. Okay, so this no label should actually dominate the other label. So that's why you should not have any imbalance in your data. So the data should be properly balanced. In case if you have 303 data points for binary classification task, and you expect it to expect at least 150 data points are actually labeled as 0, and the other 150 data points are labeled as 1. So that's the good data to work with the learning models. And then we have another command called describe on the pandas data frame. So these commands are possible only on pandas data frame. So that's why we widely use these operations on pandas data frame. Okay? So that all these things could be done in just one call to the various functions. So describe actually gives you some statistical properties associated with these non-numeric attributes. Sorry, numeric attributes. So none of them are non-numeric, all of them are numeric attributes. And since all of them are numeric attributes, these statistical properties like count, since none of them are null, none of them has null entry, so all of them are actually showing 303 as count, and then mean, value, standard deviation, minimum, maximum, and so on and so forth. Okay. And then we observe that each and every value is having different ranges of values. So that's what we observe from the statistics. So especially when you feed data to your neural network model, so you should ensure that you normalize all the input features you have. Okay. So there are again various ways with which you can normalize. So we shall see one of the normalizations which is more suitable in the context of neural network or in deep neural network. And then here we see the relation between age. We see the distribution. So we see the range of values present in each of these attributes. So age actually contains the value ranging from, let's say, from something from 20 to let's say 80. And then this sex is having only two set of values. One is 0, another one is 1. And then this REST ECG actually contains a range of 4 values. And then this Talash is having a range of values from 100 to 200 and so on. Okay. So these visualizations will help you, to better interpret the data, better understand the data. So that's why we call this more formally as exploratory data analysis. So before applying any sort of machine learning, deep learning stuffs on a data, it's better to go through or view the data from different perspective, like these graphical manner. Right. So and then in this plot we see the the relationship between age and the heart disease frequency. Okay. So is the age is being a big cause for getting heart disease. Okay. So from this plot we understand that age is not a big factor. Say for example, here we see that there is a person who is just 29-year-old who is actually diagnosed with heart disease. So whereas there is a person who is 77-year-old who is not diagnosed with heart disease. So certainly because of old age, they are not more prone to get the heart attack or heart disease. Okay. So this is one way of just comparing two attributes and how it actually participates on a target level. So age actually not much participating or not much contributing to predicting the target level. Right. So there would be other attributes which would better participate well on the target label. And here we see the correlation matrix of all the attributes against each other. So the correlation between age and age is actually said to be 1, and the correlation between age and, let's say, the sex is actually minus 0.1. So we see some values between let's say minus 1 to plus 1. Right. In case if you have a plus 1 value, then we have positive correlation. In case if you find negative values, and there is a negative correlation between those two attributes. So positive correlation is all about as some value increases, the other value also increases. So then we say that there is a positive correlation exists. In case if one value increases whereas the other value decreases, then we say that there is a negative correlation exists. Okay, so here if you see there is an attribute called old peak. When you compare it with slope, what happens is there is a high negative correlation, which means as the value of old peak increases, actually on the other hand the slope value actually decreases. So that's the way how we can essentially interpret each of these values. Right, and then we see the again relationship between age and Talash. So we observe in this plot, even though there are a lot of ups and downs, but still there is a declining trend. Okay, as age increases, the Talash actually decreases. Okay, so you can do it by this plot. So again, these plots are actually provided by something known as matplotlib, which provides a lot of better visualization techniques through which you can plot all these diagrams. Okay, all these plots. And then next coming to the training and testing. Okay, so in order to train it, we supposed to have both X part as well as the Y part. So since our data set contains both X and Y part, now I wanted to separate it out. So first I take the data set and I drop the target column and I put it in X. And then I put the target column into Y. So now my X contains 13 columns and Y contains 1 column. So earlier, if I view the data point and it is all having different ranges of values, now I want to normalize them. So in order to normalize them, I use a simple normalization called Z-score normalization. So Z-score normalization will ensure that all the elements in each of the columns present in the data set follows a normal distribution or Gaussian distribution. Okay, so there are other normalizations as well. So when you normalize this by Z-score normalization, and so the most of the data points would be centered around mean. Thus, you will have range of values from -2 to +2. Okay, some value approximately ranging between -2 to +2, because I modeled all these values in terms of Gaussian distribution. Okay, so the other simple normalization is that you can do min-max normalization. Thereby, you'll be able to convert all these actual values into the representation of values ranging between 0 and 1. Okay. Right. So it is good to normalize before feeding the data to the neural network. If you don't normalize, what would happen? The one which is having higher values is, in case the age is actually having a very larger value compared to sex. So sex is just having only 0 or 1, whereas the age is having some wide range of values. So in that case, the attribute x1 would overplay compared to sex. Okay. Similarly, if you don't normalize, then the attributes would it would overreact to the output. So we don't want that to happen. We don't want these biased things to happen. That's the reason why we normalize all the data forms. And then we divide the data into two parts. One is called train part, another one is called test part. Okay. So let's say this is our data set. Okay. Assume that I have 303 data points. Among this, I want to have 80% for my, let's say 80% for my training and 20% for my testing. That's why the test size is set to be 0.2, which is 20%. So that automatically the training size will become 80%. So 80% of these 303 data points are going to be termed as training data, and the remaining 20% of data points are going to be termed as test data. And if you want to reproduce my output, you also set the random state to be 1. And if you have different random state, then you will not be able to reproduce my output, but you will be producing some other output. Okay. And then I just supply this x and y, and both of them are going to be divided accordingly. I'm going to get x trained, the x part of training, and then x part of testing, and then y part of training, and then the y part of testing. So I'm going to get 4 such variables. Right, and then this stratify is said to be y, because when I divide it, I still want to maintain the same distribution. So even after dividing the entire 303 data set into 80% and 20%, in both 80% grouping as well as the 20% grouping, I wanted to maintain this distribution same. Okay, so that's the reason why I set stratify to S. So if the stratify is not set to S, then probably you will have there would be chance that you may have imbalanced data. So even after splitting, you ensure that the balancing should be preserved. Right. Then let me skip this because it is not required for the first neural network configuration which I am discussing. Let me skip this. Okay. So in this configuration, instead of having one neuron, I am actually having two neuron, which has to be through which you will be able to explore the other loss function and the other activation function. So let me skip for now due to lack of time we have. So let me stick to this simple neural network configuration, which has just one neuron in the output. Okay. So now I want to train my neural network model, this one. So what am I going to do here is, so I am going to construct my neural network model in this function. Okay. So I'm going to construct a deep neural network model, which is going to be a sequential model. I'm going to build it from this way. So I'm going to have my input layer, I'm going to have my first hidden layer, and then I'm going to have my second hidden layer, and then finally I'm going to have the output layer. So this is going to be a sequential model. On this sequential model, I'm going to add the layer one above the other. So first I add a dense layer having 16 neurons in my first hidden layer, and then it is going to take input from 13 dimensions because my input is of size 13 dimension. And then the kernel initializer is actually normal. So the kernel initializer is all about initializing the weight. So again, I initialize these weights again by using normal distribution. Again, there are other weight initialization methods as well, like Xavier initialization, E initialization. Here, there is simple initializer is used, with which the weights are going to be set initially. So there is some disturbance connection, right? So then then we can also use something known as regularization. There are various ways by which you can apply regularization so as to avoid model being overfitting. Okay? Especially when you train a neural network model. So what would happen because of the number of dense layers you are going to add, number of new hidden layers you add, and the number of neurons you have. So you are actually modeling a very complex function. So when you actually try to model a very complex function, so what would happen? There is a chance that your function may overfit on the data. So in very simple terms, I can say the overfitting as simply memorizing. See, simply you build a model which simply memorizes the learning point or training data points. So if it simply memorizes the training data points, so it will not be able to perform well on the unseen data. So in case assume that there is a candidate who is preparing for his or her exam. So if the candidate prepares only from the textbook and for the exam, if the problem comes from other than textbook, then the candidate will fail to perform well on the unseen problem set. Okay, we don't want that to happen. That's the reason why we use the regularization and then dropout and so on and so forth. Okay, then we use a ReLU activation function. Okay. So again, we have seen sigmoid activation function as part of this presentation. We have other activation functions as well. We have something known as tan H, and then we have ReLU, and then we have something known as leaky ReLU, and so on. Okay, so ReLU is the one that we are going to use, and if you visualize the function, how the ReLU looks, so it would actually looks something like this. Okay, the ReLU would actually looks something like this. Okay, so in the positive direction, no, it will not saturate. Okay, so it will not saturate in the positive region, whereas in the negative region it may saturate. So I use some more formal terms here. Just ignore them, if you're not able to follow, because at every epoch, we try to update the weights used in the neural network, right? So this learning has to be done for multiple epochs or multiple iterations. Okay, so at every epoch now I'm going to update my weights, right? So as and when I update my weight, sometime what could happen, some of the neurons may not be participating in the weight update. Okay, so that situation is what known as saturation. So if a neuron saturates, then the neuron will not contribute anything towards the weight update. Okay, so in that case, as long as it produces some positive value, it will not saturate, but there is a chance that it may saturate in the negative region. Okay, so in order to avoid this, we have something known as leaky ReLU, so that there is some bit leakage is provided at the negative region as well, so that it will not saturate both in positive region as well as the negative region. Okay. So that's why the ReLU activation function is here is used, and you can also use sigmoid neuron as well. You can also use sigmoid activation, so no one can stop you. You can still do that, or you can also do leaky ReLU, or you can do tan H. So you can use anything, right? And then I use something known as dropout. Again, I do the dropout, in order to avoid getting my model to end up getting overfitting. Right, so the dropout ratio here is defined as 25%, which means at every time you do the forward propagation, what you do is you are going to simply ignore some 20% of neurons in your neural network, so that all the links which are connected to those neurons, all of those weights are actually going to be set to 0, which means you just reduce the number of weights to be learned. So that's the use of dropout. And moreover, if you learn something with less information, then you'll be able to better perform. So that is another thing. Okay. So in case, assume that you are writing a neural network model so as to recognize, let's say, the handwriting character. You are developing a neural network model to recognize the handwritten character. So let's say you train your model with very fine written, handwritings. Okay, so you should not do that. Actually, you should have some handwritings, which actually does not have clear cut represent. Let's say this may be one. For a human, it may be very easy for us to interpret this as one, but we want the machine also to distinguish this, so that if it is learned with very least information, or if it is learned to interpret the bad input, then it would even work better on the very good input. Okay, in case if your upcoming input is very good, then since the model is already learned for bad images, so it will definitely work good on the good images. Okay, so that's the reason why we apply all this. Then again we add one more layer in which we are going to have 8 neurons. That's our second hidden layer. We're going to have 8 neurons, and then again we initialize all these W2 weights with normal distribution, and then we use the L2 regularization, and then we use again activation function as ReLU, and then we use again we introduce dropout of 20% and 25%, and then we add one more layer, that's our output layer, in which we have just one neuron, and the activation used here is sigmoid, and the sigmoid will actually output a real value. Okay, even the other activation functions, even ReLU will also output a real value, right? So and then I'm going to fit my model. So while fitting my model, in order to fit my model, I actually invoke this fit function on the model which I have built in the previous step. Okay? And one more thing I should set, and what is the loss function to be used? So here the loss function to be used here is binary cross entropy loss. Okay? So the cross entropy loss is actually used in order to compare two probability distribution. So you could also use the squared error loss as well here. So instead of cross entropy loss, you could also use square error loss. Okay? And the optimizer or the learning algorithm that is used by this neural network is actually known as RMS prop. So we have various optimization algorithms such as gradient descent and accelerated gradient descent and momentum based gradient descent, and then Adam optimizer, and then RMS prop, and then we have various optimization algorithms available, and in this algorithm we use RMS prop. Okay. Again, we did not much about the optimization algorithm because that itself would take about 2 to 3 hours of lecture. So let me skip for now and let me give you some insights towards the optimization algorithm. Right. So after setting all these things for the neural network configuration, so you can fit it on the trained data. So you see that I just pass X train as well as the Y train on this neural network model. So once I do this, and then moreover I run it for 50 epochs. Okay, so I start with random weight initialization, so that I measure two things at every epoch. One is the accuracy of my model, and then the validation accuracy of my model, and then the validation loss. Okay, so in the test output, in the test data, so what is my accuracy and what is my loss? Okay, so for the initial weight configuration, the loss is set to be 0.69, and then the accuracy is set to be 0.67. And then, this is not the, yes, okay, this is the first epoch. And then in the second epoch, what happens? You get to see a reduced loss and then increased validation accuracy. Okay, we expect it at every epoch, because as you run the neural network for more and more epoch, what happens is the weights are going to be adjusted. So you actually adjust weight for multiple times, and as and when you adjust weight, because we adjust weight in such a way that we want the loss to be decreased and the accuracy to be increased. So that is in the hands of the learning algorithm or the optimizer. So this optimizer will ensure that every time it adjusts the weights associated with this neural network, so it will ensure that the loss is going to be decreased every time. Okay. So now as you go down to the fifth epoch, fluctuations as well. Okay. So we shall visually also describe these values. We shall also visualize these values, and we shall see from which point actually the value actually gets increased. And we also see that the accuracy is getting increased and the loss is getting decreased, which means that there is some learning happens in this neural network. So you could also run this model, you could run this neural network, let's say for 100 epochs or 200 epochs or 500 epochs and so on and so forth, and by varying the different configurations. Okay. So why do you just stick with this configuration? You could also have other configuration of neural network, and you just observe the accuracy and the loss. Okay. So once the complete epoch is run, then you could see the accuracy and the loss. So what is its accuracy in the training data and what is its accuracy in the test data? Okay. So we see that both are going hand in hand. So we want both to go hand in hand. So we don't even want this gap between the training accuracy curve and the test accuracy curve. Okay. So and then the next plot we plot the loss. So again here is where we see that from this point probably by 14th epoch we got the reduced loss, and from 14th epoch onwards actually the loss is actually getting increased. So we don't want that to happen. So this characteristics is what defined as overfitting in the neural network. Okay, which means maybe from this point onwards, you see the loss on the training data is decreased, because the blue curve denotes the training loss and the orange curve denotes the test loss. Okay, so you see that the blue curve, the loss on the training data is keep getting decreased, even though with some fluctuations, it's still going down. Okay, we see a declining trend here. So what happens from this point, model starts actually memorizing the data points. We don't want that to happen. So again, we're supposed to handle it some way, and we have various strategies available in the context of deep neural networks, such as early stopping. So you could also early stop. Why do you run it for 50 epochs? Okay, so even though you have set it to run it for 50 epochs, so once the loss is not coming down, what you could do is you just stop at this moment. Okay, just stop with this iteration, so as to have both training loss as well as the test loss to be close to each other. Okay, so this is also a sign of overfitting. We don't want this to happen. And once you set, or once you found the right set of parameter values, okay, we get this only by running it for few number of iterations or epochs. So once you get the right set of weights, so you can stop learning and just come up, because in this case I just learn it only for 50 epochs. So once I reach the 50th epoch, I just stop my learning and then I decide my weights. So those weights are going to be used in order to apply my classifier on the unseen data. So once you apply the classifier on the unseen data, so you can actually evaluate the model. So just evaluate the performance of your model in terms of various features, and okay, so you can think of this precision as as an accuracy. So you compute precision at 0 level. How accurate your classifier is predicting the 0 class. So how accurate your model is in predicting the 1 class. Okay, so you can also visualize the effectiveness or the performance of your model in terms of confusion matrix, and the confusion matrix is defined as the amount of confusion that your model is actually making. So the amount of mistake, or how effective your model is. Okay, so since it is a 2-class classification problem, we get to see a 2x2 confusion matrix. So we have true labels being 0 and 1, and we have predicted labels being 0 and 1. And among these, let's say among 20 data points which are actually classified as, which are actually labeled as 0, among 28, 22 of them are actually correctly classified. That's what this 22 denotes. But it wrongly predicts, actual output is 0, but it wrongly predicts it as 1. So 6 such entries, data points, are actually wrongly classified as 1, but its original label is 0. Okay, similarly, coming to the other label, 33 data points are actually having label 1. Among 33, 27 are actually classified correctly, but 6 of them are actually predicted wrong. So we want this diagonal to be high, and we want this diagonals to be 0, ideally. Right? So this way you can essentially measure the performance of your classifier. So in case in this diagonal, if you could get 0 values, then